Good morning, everyone. Welcome to the fourth day of the summer school. So next up, we have Professor Akash Kumar. He's a James R. Isaac Chair Professor at IIT Bombay in the CS department. Earlier, he was a postdoc at EPFL with Professor Michael Kapralov. And prior to that, he was a PhD at Purdue with Professor Saugata Basu. Professor Akash's interests lie in the fields of property testing, spectral graphs theory, and recovery of planted structures in graphs. So with that, I'll let Professor Akash Kumar take this. Thank you.
Thank you, Brother. So can everyone hear me? Alright, so far in this summer school you have seen like the toolkit for approximation algorithms is kind of vast. There is a rich palette of options to choose from. So for example, you can use combinatorial arguments, algorithms inspired from pure combinatorial arguments. You saw how to use linear programming to, like solve a wide variety of problems. And if you were in Ravish's lectures, you probably also saw how to use semi-definite programming. We are going to see that, the list of options is endless. There is another option that you could use, and that option is essentially how to use eigenvectors and eigenvalues of a graph, the so-called spectral toolkit. How we can exploit the spectral toolkit to get approximation algorithms for some interesting problems. But let's start slowly. Okay, so first off, I want to introduce to you a graph primitive. So, you know how to explore graphs. I mean, you do depth first search, breadth first search. There is another primitive you could use. That primitive is called random walks. So let's make sure we understand what random walks are. So you're given this graph, and you start at some vertex, your favorite vertex, right? I mean, it could be anything. In this example, I chose the vertex to be this guy. That's called x0. It's the vertex u. I'm giving it a different name, x0. Right. So the idea is that, what is a random walk? So, by the way, I should emphasize that you don't have to take notes. All the notes are available on your homepage. Okay, so you can just pay attention. So what is a random walk? So it's a very simple process that takes place on a graph. By the way, is the font size visible at the back? No. Okay. That takes place on a graph.
If you can't hear it from the back, you can always come to the front.
I mean, somebody at the back said okay, and then there was a different answer, but yeah, sure. So it's a process that takes place on a graph. And what is this process? So you start off with some vertex x0, and what you do the next step is you choose a uniformly random neighbor of the vertex chosen at the preceding step, right? So this is the vertex x0. At the next step, I have 4 options to choose from, and I will choose one of those with probability 1/4 each. Okay. So I go to some random neighbor and I keep repeating this, right? So it's a random logarithmic graph where if the current vertex is denoted xt, then xt plus 1, the next vertex, is chosen to be a uniformly random neighbor of xt. Alright? So you might be wondering that, I understand very well what to do with depth first search. I understand very well what to do with breadth first search. How exactly do I use random walks? Okay, so that's the question that we'll be trying to understand deeply today. And one short answer is that you should really think of depth first search and breadth first search as procedures that allow you to explore a graph by crawling along its edges. A random walk is no different. It also allows you to explore a graph by crawling locally along its edges. Okay, and we will see just what kind of information you can mine from a graph using this random walk toolkit. Great. So suppose what I told you is that I'm going to start from a probability distribution over vertices. So it's not one specific vertex that I start from. Eventually that's what would happen though. So I have some probability distribution P sitting on the vertices, alright? And I start from this probability distribution and I want to understand, how does this thing evolve? Alright, how does this thing evolve in time? So that's the question. So let's try to track that. Let's try to think about this. So, suppose you had a complete graph. Okay? Your graph was in fact a complete graph. I'm standing at vertex 1. At next step, where could I be? Anywhere between vertex 2 and vertex n minus 1, and it's almost a uniform distribution. So this is a nice property. In one step, you can pretty much not predict which vertex I'm standing on. Alright? So we will see, like as a spoiler towards the end, that there are graphs where you don't have to walk very long. The suspense is that these graphs are bounded degree graphs. All right. So suppose I have a graph with degree 3, it's a 3 regular graph, or like a 3 regular graph, you just take like an even cycle and you connect all the diameters. Right? That's a 3 regular graph. Okay. So the idea would be that like in a graph which is 3 regular, you are standing at vertex 1, you have exactly 3 neighbors. So if you take one step of random walk, it's pretty much certain where you are. You are like one among these 3 possible places. So I can predict the chance that I will get where you are standing at the next step is very high. I will get it right with probability 1/3. Alright, if I make a uniformly random prediction, I will get where you are with probability 1/3. The suspense would be that you don't have to walk very long. You have to walk only logarithmically many steps. After which, like I will be unable to predict where you are. Alright, I would essentially have a 1/n chance of success. But I'm getting ahead of myself. So what I want to do, like next, is to like introduce to you how to think about random walks using like some common mathematical tools that you and I are comfortable with. So as a knee-jerk reaction, what you might imagine is that if you were given the task of trying to think about how to model a random walk, you might think that I have to use the toolkit of differential equations. Right? There is some probability mass sitting at this vertex, and some probability mass is going to diffuse out of it. So perhaps, and some mass is maybe going to come back because there is some probability distribution on the vertices, right? So some mass goes this way, some mass goes that way. Maybe differential equation is the right toolkit. That's what you might reflexively think. But turns out that we are in a very lucky situation. We are trying to analyze graphs. Linear algebra suffices. Okay? We will try to understand that first. So here is what I'm going to do. So let P0 denote the current distribution over vertices. And what I want to understand, so P0 is the distribution from which x0 is chosen. I want to understand the distribution from which x1 is chosen. Can anybody tell me what that would look like? The distribution P1? Can somebody describe the distribution P1 for me?
Like if you write the adjacency matrix for this graph, it will be like matrix times this probability distribution.
Good. Just we'll be a little more careful. The answer is correct and spell it. So the idea would be that P1 transposed actually equals P0 transposed times M. So why transposes? You might be wondering about this. So what's M? I have not introduced M. So M is the adjacency matrix times a diagonal matrix. So D here, D is the following matrix. The degree of the first vertex, the degree of the second vertex, on and on and on, the degree of the last vertex. It's a diagonal matrix with those diagonal entries. Sorry? Font. Okay, sorry. Yeah. Right, so D said like the matrix of degrees, like it's a diagonal matrix with degrees running down the diagonal. The idea is that I want to, so maybe it's best to take an example. So suppose I'm standing at this vertex, alright? And so maybe I'll take a shorter example though, because this example is like maybe a bit too elaborate. So this is my graph. Here is the adjacency matrix. So let's make sure that I get it right. So I will have zeros running down the diagonal, and 1 is adjacent to 2, 1 is adjacent to 4, 1 is not adjacent to 3, and 2 is adjacent to 1, 2 is adjacent to 4, 2 is adjacent to 4, good. Not adjacent to 3, all right. And then 3 is adjacent only to 4, and 4 is adjacent to everybody else. Good. So, what I want to think about is that if I start at vertex 1, for instance, at the next step I'm either at vertex 4 or at vertex 2, each with probability of half. Okay. So I want to track that. So how do I track that? I say that I'm going to divide every item in the first row by the degree of vertex 1. Every item in first row divided by the degree of vertex 1. So what I get is a legitimate probability distribution on the first row. First row is a probability distribution. Do you guys agree? Okay, it's a probability distribution. So if I want to think about the distribution P1, I already know it's 1/2 probability here, 1/2 probability here. So it kind of makes sense to multiply with P0 transposed on the left. Alright? Because that will pull out the first row. Okay? So there is this annoying issue with transposes that you have to live with, but that's life. Okay?
Sorry, the columns will not form a probability distribution.
So if it's a regular graph, they will, but if it's an irregular graph, you are absolutely correct. They will not form a probability distribution. Yeah. So yeah, the question was that will the columns not form a probability distribution? And the answer is yes, the columns do not form a probability distribution in general. Okay. Great. So now we want to start thinking about this problem a little bit more. We want to engage more with this problem. So one question that I want to convince myself of is that suppose I have a probability distribution. At the next step, do I still get a probability distribution? Let's make sure we have that right. So the best way to think about spectral graph theory is to have a little bit of physicist's intuition that I will describe a little more. So here is the claim that let P denote some probability distribution on the vertices from which, so I should also write, from which xt is chosen. So xt is a sample from P. Then what I am claiming is that xt plus 1, I can tell you what distribution is chosen from. What distribution is chosen from? I will write that in red. So that's the content of the claim, the important part of the claim. It's chosen from the distribution P transposed M. Okay.
The intention of that D inverse is to do these.
D inverse is to make every single row a probability distribution. Right? So I multiplied by the reciprocal of degree of first vertex. I will multiply it by reciprocal of degree of second vertex, reciprocal of degree of third vertex. So that's the intention of D inverse. Thank you for that question. Alright. So let's prove this result. Let's see. Somebody is claiming to you that P transposed M is a probability distribution. Okay, I mean that's all I need to show, I guess. So how do I show that? So first of all, I claim that in P transpose M we will not see any negative numbers. If P transpose M is supposed to be a probability distribution, there should be no negative numbers in there. Can anybody prove for me why there are no negative numbers in P transpose M? I mean, just it's an easy question, so feel free to shout out the answer.
Because when you do M transpose P, for example, you are just summing up non-negative numbers.
Yeah, there is no negative numbers anywhere, right? So P transposed M is non-negative, at least that part checks out. Okay, now I need to do a harder bit, that the entries of P transpose M add up to 1. There is a beautiful trick. You want to add entries in some non-negative row vector, alright? There is a vector that you can take dot product with which will add all the entries. What vector am I thinking of?
All one vector.
All ones vector, right? So notice that the sum of entries of P transposed M is precisely P transposed M times the all ones vector. But this is beautiful. M times the all ones vector is what?
All one vector.
Is the all ones vector. Does everybody see that? Right? All the rows of M, they add up to 1. So this is P transposed 1. But P was a probability distribution. This is sum of entries when P add. That's 1. Voila. So that's a pretty easy verification. So Markov matrices, these matrices capital M of the form D inverse, these are called Markov matrices. So let me write that name. Markov matrices, right? So Markov matrices map probability distributions to probability distributions. Some things are type checking, we are making some progress, we are going somewhere, we don't know where, but let's see. So if you were a physicist, you'd be interested in answering, let's say, the following question. I have a sponge, an actual sponge, all right? That thing that you use to wash dishes, that scrubber. Okay. So I have a sponge. I dip it in some water, let's say colored black. I squeeze it well, and I take it and put it on the table. I look at this sponge after 1 or 2 hours. Some black patterns have emerged on the surface of this sponge. Okay. What you want to understand is, as a physicist, you are interested in understanding, can I develop a theory which tells me what patterns emerge? Right? So that's the question that you might be interested in, for instance, if you're a physicist. So here is like a cartoon model that physicists use to answer such questions. So they pretend that a sponge is in fact made up of several mini sponges. Alright? And 2 mini sponges that are close by, they are connected by an edge. Okay? If many sponges are far off, they are not connected by an edge. So that's a very simple cartoon picture. And now they think that, like, when you put it inside some black colored water, you squeeze it well, took it out and put it on the table, there is actually some random walk taking place over this graph of mini sponges. Okay? So random walks are useful. Physicists use it all the time. If you think about any diffusion process is just a random walk. Okay? So, like for example, diffusion process, you might have heard about this term in your biology classes, chemistry classes, and you have forgotten about it. I have. So, yeah. The idea is that, if you want to understand the limiting pattern that this black formation is going to take on the surface of the sponge, you are going to rely on this random walk toolkit, that there is some unit of water, let's say 1 unit of water, held inside your mini sponge, held inside your sponge, and that water is doing a random walk. Okay? That's how you think about it as a physicist. As a physicist, you know the answer already, that there is some limiting pattern that does emerge. Alright? You know the answer already. You want to develop a mathematical theory that explains what kind of patterns are going to emerge. Is there a probability distribution over the final patterns that emerge on the surface of the sponge? That's the question you're trying to target. So let's see how a physicist can take some help from computer scientists to resolve this question. Because physicists can never really do anything on their own. So,
I have a simple question.
Yes.
My mental image of your random walk is of one person moving around on the graph, whereas this diffusion process seems like you're leaving things behind and
That's
locations are
correct.
going on. So is there a,
Yeah.
do you have a different mental model for how you think
No,
about it?
so that's a great question. So, Professor Neil Dhara is asking the following, that it is often very convenient to think about random walks as there being one single walker who is hopping from one vertex to neighboring vertices. So what she's asking is that, in this sponge picture, it seems that as if there is not one single walker, but there are several molecules walking together. So how can I think about it, using the random walk analogy? So the response is just this, that, at the end of the day, you are tracking probability distributions anyway, right? So you can pretend that this probability distribution is in fact made up of this fluid, this water, right? So at the end of this discussion, the random walk toolkit is already versatile enough, rich enough, accommodating enough to accommodate not just one single walker, but to accommodate a distribution of walkers, multiple of many of them walking through at the same time. Right? That's a great question actually. So let's see, when we already know the answer, what we can do. Okay? So the idea is something like this. We already know that some limiting phenomena is what I want to show. Okay? This limiting phenomena somehow involves my Markov matrix. That I know. So maybe, just maybe, the limiting phenomena, so possibly our limiting phenomena can be understood by looking at expressions of the following form. As time goes on and on and on, I take my Markov matrix to some large power and I want to understand what does that limit look like. I understand there are many of you who perhaps have not seen limits of functions of matrices. But don't worry about that, because physicists don't worry about that. They break rules all the time, so yeah. Okay, So this is what you want to understand, and like as of right now, what I've told you is that like this is some mysterious object that we don't understand. But let's not worry about it. Let's just try to think, when can we expect a matrix to have the following property, that power iterations of that matrix stabilize, some limiting phenomena emerges. So can you expect, the question is, can you expect the following matrix to have very nice properties, power iterations on this diagonal matrix to stabilize? Yes, no? Many people are nodding no. Why?
If you take m power t, then the entries will be
Good, good. So m power t, 2 power t, 3 power t, entries blow up. So I already know that I cannot expect the power iterations to stabilize if, you know, stuff blows up. So, and like the stuff I'm interested in is actually the eigenvalues. Right? This matrix is eigenvalues 2 and 3. So I really would like, as a first step, to think about matrices that have eigenvalues. So, like, this is a fact that I'm going to state. I hope that you are not too uncomfortable with it. That let M be a real symmetric matrix, then it always has eigenvalues, real eigenvalues. All eigenvalues of M are real. There is a much more richer theorem that you could actually state, that it has like an entire collection of eigenvectors, and M could be written in the form U sigma U transposed. Okay. So I'm going to assume that fact. So like, suppose this matrix M had eigenvalues that are larger than 1. The power iterations will never stabilize. It had eigenvalues smaller than -1. Alright, power iterations will never stabilize. So if a physicist wants to expect that all the eigenvalues that are finally limiting phenomena should emerge, that physicist better prove that all eigenvalues of M lie between -1 and +1. Right. I misspoke. If physicists will not prove this, we will prove this. We will finally look at that, but yeah, I mean, we are starting as crudely as possible. But Professor Neil Lehra teased a very interesting question that, like, you know, if I start with different probability distributions, do I expect different limiting law to emerge? Let's keep that aside for a while. We will unpack that slowly when we get there. Good. So here is our revised objective. We want to help out our physicist friend, and we want to prove to this friend that, like, you know, all eigenvalues of capital M lie between -1 and +1. That's what I'd like to prove for my physicist friend. Okay? How do I do that? Okay, first off, I'm going to make a simplification. I'm going to assume that my matrix is in fact symmetric. Now, I have a Markov matrix corresponding to random walks on a graph. In what situations will this matrix be symmetric? What should hold true about my graph for the Markov matrix M to in fact be a symmetric matrix?
undirected graph.
Undirected, sure. Something more. Okay, something more. Okay.
Connected?
Yes, all connected components must be regular. If you want capital M to be symmetric, all connected components must be regular, right? So the observation is that if M is a symmetric, is a symmetric Markov matrix for random walks on a graph G, then all connected components of G must be regular. But you're right, it's good to think about connected graphs, so we'll pretend that our graph is connected and regular. Alright, so in the rest of the discussion, I'm going to always pretend that my graph is connected and regular. Everything that I'm saying generalizes to undirected graphs, and maybe some of that like you will see in the exercise session today. Okay, so let's move on. So again, I emphasize my assumption is that my graph is connected and deregular. Perhaps I should write that assumption. That's what I will assume for the rest of this class. Okay, I want to show that all eigenvalues of m lie between -1 and +1. Let's compute some eigenvalues of m. Why don't we? Yes.
Follow the
Great. So look, I was just making like some theory at a very high level. We understood that if we take power iterations on my Markov matrix, these will not stabilize if your eigenvalues exceed -1 or +1. Okay. But now I want to be thinking about those matrices which have eigenvalues. So the simplest mantra that I know is that if your matrix is a real symmetric matrix, it has eigenvalues. Okay. So I want to help my physicist friend, but I tell him that look, cut me some slack. I'm going to provide you a theory of random walks, which will tell you that random walks stabilize provided your matrix is symmetric. My matrix is known to be Markov matrix. I require my Markov matrix to be symmetric. The question is, when can this happen? When are Markov matrices for random walks on graphs symmetric? The response is that these guys are symmetric precisely when your graph is a regular graph. Because remember, your adjacency matrix is symmetric, right? Aij is always equal to Aj in adjacency matrices, right? So if I look at Aij divided by D, it will be equal to Aj divided by D as well, provided I divide by the same number D everywhere. So my graph is regular. Okay? Great. So that's an important clarification. Okay, alright. So with all of these assumptions, we are now ready to help out our physicist friend. But first we ask one thing. Is there an eigenvalue of m that is easy to compute?
eigenvalue 1.
Okay, so,
All-one vector.
yeah,
You take all-one vector.
Great.
Because m is Markov matrix.
great. So here is the observation that the number 1 is always an eigenvalue of a Markov matrix. And why is that? All rows of m add up to 1. So if you multiply m by the all ones vector, what do you get? Lambda, which is equal to 1 times the all ones vector back. Alright, so 1 is always an eigenvector. Alright. Yeah, before I make progress, I want to get more confidence. Like, I'm a bit worried always that I might get something wrong. So perhaps I might look at an edge. This is maybe the simplest graph I can imagine. Hey, I can imagine a simpler graph, just one single vertex, but there is no fun in that. So I have this graph. I want to think about Markov matrices for this graph. So Markov matrices for this graph, fortunately all the degrees are 1, so you don't even have to divide. Right? M equals the adjacency matrix equals 0, 1. Brilliant. This guy, you already know 1 is an eigenvalue. What is the other eigenvalue? Why? Why is -1 an eigenvalue?
You take lambda square minus. If
You take the trace. Easier. Or you take the determinant. Both things work. Good. So that the other eigenvalue for this guy is -1. Now I have some confidence that at least for a very simple example I took, eigenvalues were 1 and -1. But I want to show this in general, that all eigenvalues are trapped between 1 and -1. How do I show that? So let's have a lemma. Yeah, I mean that's the objective. So yeah, I was going to precisely restate this thing as my lemma. But that's something that I can prove now. Maybe somebody can help me. How will you prove this? Any guesses? How can we prove that all eigenvalues of capital M, where capital M corresponds to the Markov matrix of a connected deregular graph, all eigenvalues of this guy lie between -1 and +1.
Take something greater than +1 to show that it cannot be really coefficients.
Okay, so what we talk about is there is an idea there. So let's try to formalize it. Is there a question? Okay. Yeah. So here is what I would like to state. So we will prove the following. So maybe I should call it game plan. So the game plan is that I will show that the identity matrix minus m is positive semi-definite and the identity matrix plus m is positive semi-definite. By the way, how many of you know what PSD matrices are? Okay. Like there are those of you who do not know what PSD matrices are, so I'll remind you. So PSD matrices are symmetric matrices, all of whose eigenvalues are greater than or equal to 0. All of whose eigenvalues are non-negative. There are several equivalent characterizations. Unfortunately, I cannot run through all of them. But yeah, I mean that's pretty much what the. So maybe I will like write a reminder here that a matrix M, which is symmetric, all entries being real, is PSD if X transposed MX is greater than or equal to 0 for every vector X. So no matter what vector you give me, this quantity, this is called a quadratic form, always evaluates to a positive number. This is the definition and equivalent definition of a PSD matrix, not in terms of eigenvalues. So yeah, this is what I would like to show. That I minus M, so somehow the matrix M is trapped between negative identity and positive identity. And I want you to like take this as evidence that like somehow it's trapped between minus 1 and plus 1. We'll make everything formal, right? Somehow all the eigenvalues are trapped between minus 1 and plus 1. Let's prove this. Okay, this is like not that bad. So remember, my graph is deregular. So if you look at the identity minus M, this is the same as identity minus adjacency over the degree, which is the same as di minus a over little d. I want to look at the numerator, and I want to introduce a very interesting matrix. Okay. So consider the numerator, which is equal to the matrix with degrees running down the diagonal, capital D, minus A. So whatever claim I am going to make now, the claim is that D minus A is a PSD matrix. Okay. This claim holds even for irregular graphs. So I will prove this claim even for irregular graphs. Alright. So the tiny little claim over here is that D minus A is PSD. This matrix is very important. It's so important that it is given a name. It is called the Laplacian, capital L. And you will see why this matrix is important in a bit. One of the reasons why it is important is because it allows you to reason about eigenvalues of capital M. That eigenvalues are trapped between negative 1 and positive 1. Okay. So let's see. I'm looking at the numerator. So what I would show is that the eigenvalues of the numerator are trapped between negative d and positive d. Right? Therefore, if I scale everything down by 1 over d, eigenvalues are trapped between negative 1 and positive 1. Okay. So that's what I want to show. So let's see how you will do that. First, I will claim that d minus a is PSD, and that's easy enough. Right. So here is some graph. Maybe the graph that I took earlier. I guess this guy was called 4, 3, right? So what I want to do is I want to first write out the adjacency matrix for this guy again. I want to write the Laplacian for this guy again. And I want to think about Laplacians emerging in a slow manner. So here is the adjacency matrix. So 0 is running down the diagonal. Then 1 is adjacent to 2, 1 is not adjacent to 3, it's adjacent to 4, 2 is adjacent to 1 and 4, right? 3 is adjacent to only 1. Yeah, 3 is adjacent to 1, so I got that wrong. And like 4 is adjacent to 2 and 1, right? Yeah. So I believe I have that right. So now let me write out what the Laplacian looks like. So Laplacian, pretty easy matrix, right? I have to negate everybody in capital A. Laplacian is D minus, I have to negate everybody in capital A. And I have to put degrees running down the diagonal. So degree of 1 is 3. Degree of the vertex 2 is 2. Right? Degree of vertex 3 is 1. And degree of vertex 4 is 2. Everybody else, I'm going to negate those. Negative 1, negative 1, negative 1, negative 1, negative 1, negative 1. Why? Yeah, sure. Good. That's great. So that's my Laplacian. You can observe that all rows of Laplacian add up to 0. Okay? That's an easy verification. I want to now write down this Laplacian emerging slowly. Okay, so let's explore what I mean by that. So here is what I want to do. I'm going to look at every edge and I'm going to think about what a Laplacian for that specific edge looks like. Okay? So I focus on just one edge. So there are only 4 edges to think about. So first I look at the edge 1, 2. Okay? And what does the Laplacian for edge 1, 2 look like? That's what I want to think about. So the Laplacian for edge 1, 2 looks like the following. That's it. Zeros everywhere else. Okay? That's what the Laplacian for edge 1, 2 looks like. Okay, so now I want to look at the Laplacian of edge 1, 4. What does that guy look like? So Laplacian of edge 1, 4. Maybe I want to give myself more space. Laplacian of edge 1, 4. It looks like another one over here, right? And this is 4, right? So yeah, minus 1 over there, minus 1 over there. These two ones, I add them up, becomes a 2. Okay. Now let's look at, so I looked at Laplacian, I want to look at Laplacian of 2, 4. So Laplacian of 2, 4, what does that look like? So here is a one that's going to be supplied over there, another one that's going to be supplied over there, then minus 1 in this location, minus 1 in that location, so that becomes 2, minus 1, yeah. Okay, finally, I look at the edge 1, 3. So 1, 3, so what does that look like? So again, I put a plus 1 over there, so that becomes a, so 2, 1 maybe, that's the way I was writing it. Then I have a minus 1 over there, a minus 1 over there, a 1 over there. So that becomes a 3. And lo and behold, your entire Laplacians emerge. Every place else that has not been filled, you just put zeros. So what we have discovered is that the overall Laplacian is the sum of these baby Laplacians. That the overall Laplacian is sum of Laplacians of these mini edges. Okay?
The baby Laplacians are just the submatrix induced by those rows.
Yes, yes. Right? Just you put in that structure 1, negative 1, negative 1, 1 over like all those structures. And so what we have observed is that the Laplacian is the sum of baby Laplacians. This is great. It's an easy verification that all the baby Laplacians, they are positive semi-definite. Sum of positive semi-definite is positive semi-definite. Therefore, D minus I is positive semi-definite. And why is LE positive semi-definite, you ask? So remember, LE for a single edge E has this pattern. So if you take quadratic form with any vector x1, x2, so notice that x transpose LEX equals x1, x2 followed by this Laplacian followed by x1, x2. You do this computation, you get x1 minus x2 whole square. So this thing, many Laplacians are in fact positive semi-definite. The sum of many Laplacians is therefore also positive semi-definite. Alright? So D minus A is positive semi-definite. That's great to know.
And just for type checking, L is an n by n matrix.
L is an n by n matrix. With everything else 0. Yeah, yeah. L is an n by n matrix. Yeah. Thank you. Okay, so I'm going to erase this because like this was just a proof by an example. And like you can easily see that this generalizes. Okay. So LE, the same rule. The diagonal matrix minus the adjacency matrix. So I have this edge E. 1, 2. So in this example, I have this edge 1, 2. What I do is that I am revealing the graph, let's say piece by piece. So I reveal the edges one edge at a time. So first I reveal, let's say only this edge. So far in the revealed graph, the Laplacian revealed graph is diagonal matrix minus the adjacency matrix of the revealed graph, which has precisely that pattern 1, negative 1, negative 1, 1. Right? That's what baby Laplacians are. So we have proven that D minus A is PSD. So it implies in the D regular case, Di minus A is positive semi-definite, Di minus M, sorry, Di minus A, Di minus M, sorry. So this means that all eigenvalues of A, they cannot exceed D. If any eigenvalue of A exceeded D, I am in deep trouble, right? Because then this thing will become negative. So no eigenvalue of A exceeds D. Brilliant. Similarly, you can show that Di plus A is also PSD. The exact same argument goes through. Okay? Di plus A is also PSD. Therefore, all eigenvalues of capital A are trapped between negative D and positive D. Therefore, all eigenvalues of D minus A over D, they are trapped between negative 1 and positive 1. Okay? So, we have helped out our physicist friend. Brilliant. Okay. But our physicist friend had a somewhat stronger demand. He wants reassurance that everything is going to track out. That this diffusion process taking place over the surface of the sponge is eventually going to converge. That's the guarantee our physicist friend wants. So let's see if we can make good on our promise and if everything checks out. There is a problem. There is a big problem. So let's see what the problem is. So again, let's revisit our favorite graph. Just an edge. Our entire theory, cock and bull it may be, is derailed by this graph. Just an edge. It's just an edge that throws our entire theory out of the window. So let's see what I mean by that. This guy is a very annoying graph because I remember that the Markov matrix M was the same as the adjacency matrix, which was 0, 1, 1, 0. The eigenvalues of this guy were plus 1 and minus 1. Right? Eigenvalues are plus 1 and minus 1. Say lambda 1 is 1, lambda 2 is minus 1. The first eigenvector u1, the first eigenvector is called u1, the second eigenvector is called u2. Alright, so what I know now from our linear algebra, if that's fresh with you, what we know is that capital M can be written as lambda 1 u1 u1 transposed plus lambda 2 u2 u2 transposed, which is the same thing as saying it's u1 u1 transposed minus u2 u2 transposed. Remember, u1 u2 are eigenvectors, they are orthogonal. Okay? So this is like some linear algebra that I am leaving for you to go and check back. So if you're not comfortable with this part of linear algebra, I'm sorry, I won't be able to cover that because there is something more that we need to see. So u1 u2 are orthogonal. The inner product between them is exactly 0. So what you observe now is that if you have to take higher powers of M, then M squared, what does that look like? So it's u1 u1 transposed minus u2 u2 transposed times itself. So let's see what that is. So u1 transpose hits u1, that becomes a 1. Right? That becomes a 1. So you get u1 u1 transpose back. Minus u2 transpose hits u1, that becomes a 0. Because these vectors, they are orthogonal. u2 transpose u1 is 0. That's great. u1 transpose u2, that becomes a 0. And this minus, that becomes a plus. So this becomes plus u2 u2 transposed. In fact, what you would observe is that even powers of M, all of them are exactly this expression, odd powers of them are all exactly that expression. So the matrix keeps shuttling. There is no limiting phenomena that can ever emerge. Right? All even powers of M are exactly that expression, all odd powers are exactly that expression. Nothing stabilizes. Alright? This is not very unexpected though. So if you paged out because there was too much linear algebra earlier, here is an opportunity to page back in. Ignore all of that. This thing can clearly never stabilize. At odd steps, I'm at vertex 2, at even steps, I'm back at vertex 1. Right? At all odd steps, I go there, at all even steps, I go there. How can this stabilize? I keep flip-flopping. Right? No limiting phenomena emerges. So our physicist friend is very unhappy that so much ado for nothing, but something nice has happened. What we can tell our physicist friend is that, like, even though this did not work, but I can easily fix this. I know that I have to live with the eigenvalue 1. All Markov matrices have eigenvalue 1. I will arrange for a situation to happen which will enforce that negative 1 is never an eigenvalue. Okay? So here is what I do. Fix 1. Consider m prime equals identity plus m. Looks like I had a brilliant brainwave. I just decided to shift all the eigenvalues by 1 to the right. Brilliant. Negative 1 is no longer an eigenvalue, but positive 1 is no longer an eigenvalue. That was a stupid fix. That does not work. Fix 2. Consider defining a new matrix W equals identity plus m over 2. Negative 1 is gone now. That's not an eigenvalue anymore. Identity plus m, we already discovered identity plus m is PSD. I minus m was PSD, I plus m was PSD. That's what we wanted to show. So this guy is PSD. The smallest eigenvalue is 0. Right? So all eigenvalues are at least 0 or bigger. Alright? All eigenvalues are trapped between 0 and 1. The largest eigenvalue is exactly 1. Things look as if they are going exactly the right way. But we want to be sure in our bones that everything is alright. So I claim that you can view this matrix W as doing something to the graph. What is it doing to the graph? This matrix W is doing something to the graph. What is it doing to the graph? Your graph is 3 regular. What's happening in the graph picture?
So at least at this edge, it seems like you're allowing people to stay back on the same vertex.
Good. Self loops. Right? So what I'm doing, what I plus m over 2 does, is that at each vertex, it adds loops. It adds 3 loops at every single vertex. The idea is that, with probability 1/2, I will stay at this vertex with probability. So I over 2 contributes the half probability of staying at that vertex. So my degree is 3, right? But I want a chance of 1/2 to stay at this vertex. So I must add 3 self loops. Okay, so that's what I'm doing. At every single vertex, I'm adding exactly these self loops. Right? So things look alright, and things are alright. That's what we'll prove now. Okay? So W is the matrix that you wanted to improve. So the claim is that the power iterations on W in fact converge. But it gets even better. So remember the question that Professor Neil Hara asked, that if you start with some probability distribution, P0 on the vertices, what limit do you converge to? What we will show is that it does not depend what distribution P0 you start with. The limiting distribution is always the same. It's a unique distribution that you always converge to. So the claim is, so the way this claim reads in my head is W is the matrix I wanted. But yeah, that's not what you write. You say that, like, for all start distributions, P0, you have limit of, like, W power t tending to infinity, times P0. So now I can multiply P0s on the right. W is symmetric. It does not matter whether I put P0 on left or right. Right? So I put it on right. This thing converges to the all ones vector divided by n. So the limiting distribution is always the same. That's what we'll prove. Let's see how we can prove this. So it is this proof that will motivate the need for cutting graphs. So you want to cut graphs, why? This proof will tell you why. So there is a certain part that I will skip. That part will be deferred to the cutting graphs part if I can get to it. So let's see.
Single edge, you're saying if I started with a 99% probability mass on 1 and 1% probability mass on 2, I will eventually get to half.
Eventually in the limit will converge to 1/2. Even that will not depend on P0. Everything will depend on properties of it. So there is something that I will leave as an exercise. So I will in fact think about a start distribution that puts all its mass on your favorite vertex. You could choose this vertex adversarially if you wanted to. And I claim this is enough. This is without loss of generality. So without loss of generality, you can think about those probability distributions. All of this probability mass is on one single vertex, possibly chosen adversarially. Does not matter. So here is the proof. Without loss of generality, assume that P0 is in fact the indicator for a vertex U, for your favorite U. Okay, I still I promised earlier that we'll be trying to make sense of power iterations on capital M. We're trying to think about power iterations on capital W. And the way I think about power iterations on W coming to a limit is by in fact looking at this situation. I'm looking at vectors coming to a limit, which makes more sense for most of us. Even matrices make sense, but this thing makes like more transparent sense. So let's see how we can prove this. So here is what I would show. We will show that limit t tending to infinity, w power t times 1 sub u minus the all ones vector over n, this thing goes to 0. So I should tell you that I'm going to make an assumption that that I defer to the cutting graphs part. So what I'm assuming is that lambda 1 minus lambda 2 is so lambda 1 is 1, remember, lambda 1 is 1, that's the largest eigenvalue. So I'm claiming that the second smallest eigenvalue is kind of bounded away. Let's say it's 1 over n square or something. So what I'm claiming is that it will never be less than 1 over n square. So that's an assumption I'm making. It could very well be equal. So if they're not equal, if they're unequal, if lambda 1 is not equal to lambda 2, the gap is at least 1 over n square. So that's something that I'm going to assume. Okay. So in fact, so I'll be a bit more careful. So it turns out that I don't even have to make this assumption. If your graph is connected, lambda 1 minus lambda 2 is at least 1 over n square. So that's a fact that we'll prove later is at least 1 over n square if your graph is connected. And I'm writing eigenvalues in decreasing order. I'm writing eigenvalues of W in decreasing order. So here, lambda 1 greater than or equal to lambda 2 greater than or equal to lambda n denote eigenvalues of W. So there is no assumption I'm making, I should be careful. There is no assumption I'm making. For the purposes of this proof, I'm going to use this fact. This is a fact that I will prove later, I would like to prove later, I do not know if I have the time. So we'll see. So that's a fact that we are going to use. So W is I plus M over 2. I'm sorry, I erased that. Okay, that's W. Good. So what I'm going to do is I'm going to write 1 sub u in the eigenbasis of W. Okay. So let V1, V2, Vn denote the eigenvectors of W. Sorry, looks like I'm writing in Farsi or something, right to left. Yeah. So write 1 sub u as the sum of these vectors, right? So express 1 sub u as a linear combination of the eigenvectors. Okay, that's all I'm doing. So now I want to think about what value does this length take? As the random walk progresses, there is a certain length I'm looking at. The length of the current probability distribution on vertices minus the probability distribution which puts the same mass everywhere, minus the uniform distribution. So that's what I'm looking at. Okay, there is one thing I'm interested in. I'm interested in the value C1. So what is C1 equal to in terms of the eigenvectors? Can you tell me what C1 is? Give you a hint, but I'll wait.
It will be 1.
Summation Ci squared is 1, right? Because this vector, its Euclidean length is 1, right? So summation Ci square is 1. What is C1? C1 is an inner product between some two vectors. Which two vectors? C1 as an inner product between two vectors written on the board. What vectors are those? V1 and? 1. Good, good. So summation Ci square is 1. Remember, V1 like is an eigenvector, right? So what I would like to do is, in order to define C1, what I can do is that I can take C1 to be the inner product between V1 and 1U. So 1U is a vector which has a single one in the UH coordinate. Right? A single one in the UH coordinate. V1 is an eigenvector. So it turns out that like you can say something about V1. So this is like essentially the UH coordinate of V1. This is the UH coordinate of V1. Right? Because 1U is a very special vector. Just a single one in the UH entry. Right? All the other vectors are. So you don't just take this dot product, only the UH coordinate of V1 survives. But I claim that you know something more about V1. You know something more about V1. What do you know about V1?
Should be all one vector. This one's
Great. So remember how, so what's your name?
my name is Praveen.
Praveen. So remember, Praveen pointed out for us that the leading eigenvector is the all ones vector. Right? So V1 is the all ones vector. Okay? But I want to normalize it. I want to normalize it to have length 1. So V1 is in fact 1 over square root n in every single coordinate. V1 is 1 over square root n in every single coordinate. In particular, the UH coordinate is 1 over root n. Right? So this is 1 over root n.
This is where the choice of U doesn't matter.
Yes, yes. Good point. Good point. Right. So V1U is 1 over root n. And now I will continue writing in Farsi. Urdu also you write this way, no? Okay. So maybe Urdu. Okay, so that's great. I know what C1 is. And so what I can like think about like this vector 1 over n is like in the following language. So note w to the t times 1 sub u is like, you know, summation Ci Vi. So I just want to show that I get is equal to w to the t times summation Ci Vi. So what does that guy equal? So this is like, you know, w Ci lambda I to the t Vi. Right? Because Vi is an eigenvector, so w Vi is lambda I Vi. W square Vi is lambda I square Vi. On and on and on. Right? So this is what that expression equals. So let's write this as C1 lambda 1 to the t V1 plus everything else Ci lambda I to the t Vi. Lambda 1 is 1. C1 we just saw was 1 over square root n times V1. Okay. V1 I know was 1 over root n in every single coordinate. This guy is all 1 over n. Brilliant. I moved that guy over to the left. That expression emerges. Brilliant. So this tells you. So let me write it slowly. W to the t 1 sub u minus summation Ci minus all 1s over n is equal to summation Ci lambda I to the t Vi. Now I put knobs on both sides. Triangle inequality. Alright? That's your friend. So I claim this is at most the sum of Ci lambda I to the t Vi. Remember, lambda i's are eigenvalues of W. W is positive semi-definite. No eigenvalue is below 0. Alright? All the other eigenvalues on the other hand are bounded away from 1. They are at most 1 minus 1 over n square. Right? All other eigenvalues are small. Ci, all Ci's are like, you know, less than 1. So this quantity is less than equal to this quantity, this expression, I will call it star. So what you have is that star is no larger than, you know, what happens if I just get rid of Ci? So I'll get rid of Ci. Right? Lambda I to the t Vi's are anyway unit vectors, so I will throw them away. I don't care about unit vectors. And like, call gap between lambda and lambda to epsilon. So like all lambda i's, they are at most 1 minus epsilon. All lambda i's, they are at most 1 minus epsilon. So this is like, less than equal to 1 minus epsilon to the t. Yeah, so less than equal to n times 1 minus epsilon to the t. As t goes to infinity, this thing goes to 0. Okay. So we finally helped our physicist friend, but like in order to do this, we needed to make an assumption. We relied on that fact. And that's what I'd like to prove, but I don't think I have the time to prove it, but like I'll set up some more ground to make sure that we are able to like, at least understand the story behind that proof. But first I want to make sure, does everybody follow this proof? Any questions about this proof? I mean, like what you have seen is like one very deep result in the theory of random walks. Okay, there is more comments to make here. So like one comment is that like, it's as if the final limiting distribution has no memory of the starting distribution. Right? This is called the forgetting property of random walks. Okay? And another thing that you might realize is that, look, I took limit t tending to infinity. So let me use a stupid language. Limit t tending to infinity plus 1. Okay? That's the same thing. Right? Forget the final distribution that you end up with does not change. This is suggesting something rather intriguing. So what this suggests is that the limiting distribution is in fact an eigenvector. And that eigenvector is very important, we give it a name. Stationary distributions. So it's typically denoted pi. A vector pi in Rn is called a stationary distribution. So in fact I should write more. It's a non-negative vector with L1 norm 1, all the entries adding up to 1. It's called a stationary distribution if m times pi equals pi. Or if I'm being more careful, I will write pi transposed m equals pi transposed. Okay. So typically you should talk about a stationary distribution, not the stationary distribution. But there are a lot of situations, very simple assumptions under which stationary distribution is in fact unique. So pretty much the situation we considered as stationary distribution was unique. And turns out that this stationary distribution has a nice property. What I'm telling you is that my current distribution is pi. You do one step of the random walk and nothing changes. Y stays invariant with respect to the transition steps of the Markov chain, of the underlying Markov matrix. Yes? Sorry?
That should be W?
Yeah, that should be W, but I mean that's fine. For Markov, since I am writing a stationary distribution, that is fine. Okay? But you are right, correct. If I am being extremely pedantic, that's what I would have written. But the thing that I want to emphasize is again, like look at the following picture. The current distribution P0 is pi. The next distribution P1 is also pi. So suppose I ask the following question, that suppose my current distribution is pi and I am looking at the following picture. This is my graph, this is some subset S, that's some subset S complement. So some edges go across. Suppose the mass sitting over here is something, maybe I will call it pi of S. The mass sitting over here is 1 minus pi of S or pi of S complement. Right? That's the total probability mass over here, that's the total probability mass over here under the stationary distribution. At the next step, some mass flows from left to right. Right? So let's say that the mass that flows from left to right is called little l. If the mass that flows from right to left is called little r, what can you say about little l and little r?
Both should be same.
They should be same. Mass that flows across a cut is same across any given cut. That's quite exotic behavior, right? That's a pretty exotic behavior. No matter which cut you take, the mass going from left side of that cut to the right side of the cut equals the mass coming back in. This thing is called a balance condition. Okay? So this is balance condition. Which says that mass across a cut equals in both direction. Or they are equal in both directions. I mean, There is some problem with my grammar here, but forgive me. Right. So the next thing that I want to state is that sometimes an even more exotic situation is true. This is fairly exotic, that I have 2 power n cuts, 2 power n minus 1, and the mass across any cut going from left to right equals the mass coming back in. But sometimes an even more exotic condition is true. This, if you think this is exotic, you have seen nothing yet. So let's see what I mean by that. So there is what we call the detailed balance condition. So the balance condition that you just saw is true for even directed graphs. Even if a directed graph admits a stationary distribution, the mass traveling across left to right should equal the mass coming back in. Detailed balance condition is what all undirected graphs exhibit. All undirected connected graphs exhibit detailed balance condition. So what that means is that forget about thinking about every single cut, just look at a single edge. So you have an edge x comma y, and the mass that vertex x carries is called pi x. The mass that vertex y carries is called pi y. X has a few neighbors over here. Y has maybe some more neighbors over there. So what I am going to claim is the following, that the mass that travels from x towards y along the direction xy equals the mass coming back in. Nothing can be more ridiculous than that. This is too exotic. But this is something that every single undirected connected graph exhibits. That pi x times the mass that x dispatches towards y. So the mass that x dispatches towards y is 1 over the degree of x. This equals pi y times 1 over the degree of y. And it turns out if detailed balance condition is true, the balance condition is also true. If you are sending equal mass back and forth along every single edge, you are sending the same mass back and forth across like all the edges of a cut. Detailed balance explains balance. Okay. This is too exotic though. I mean, I can't help but be scandalized by this every single time I stare at it. This is too beautiful. Okay. Good. So let's keep going. So now what this was an aside. We did not really need this, but I find this aside like almost irresistible. This is just one of the most beautiful things in math I have seen. So
what are the assumptions you make here that it's connected
regular you don't even need regular. So even you can sacrifice regularity. That pi is the stationary distribution. That's it. So this is just too beautiful. And by the way, if you have a Markov matrix which satisfies the detailed balance condition. So you have a Markov matrix and some mysterious vector, you do not know how you got it, maybe somebody gave it to you. So probably for a Markov matrix you received maybe some mysterious vector from Neil Dhara. And now what happens is that I verified it for you that this mysterious vector satisfies the detailed balance condition. Then this mysterious vector is the unique stationary distribution. So if any Markov matrix satisfies, so like this is just some more irresistible things I am mentioning without proofs. Okay, so I did not give you a proof.
That feels like that better be true because otherwise non-stationary things.
That better be true. Yeah. So like again, I want to make sure that the way this setup worked is that I had a Markov matrix in mind, and that's all I had. I did not have anything else. I had not even bothered computing the stationary distribution. What Professor Neil Dhara did is that she gave me a gift. She gave a mysterious vector. I verified that this mysterious vector satisfies the detailed balance condition, and then lo and behold, this is the unique stationary distribution. Voila. Okay. So now I want to finally go towards cutting graphs, and most likely I am already out of time. Arka would probably know better, doing figures in 20 minutes. Sorry. I started 5 minutes late.
Yeah. 26 minutes we will take.
Okay, thank you. Yeah, so that's a tall order, but let's see how far we can go. The only thing that I hope to get across is the story, if not the proof. Okay, cutting graphs. So let's try to cut graphs that are already cut, so you don't have to do anything. Disconnected graphs. I mean, they're the best graphs, right? Okay, because they're so easy to cut. So again, here is the idea. I give you a graph. It has at least k connected components. Let's look at the Laplacian, because why not? So let L equals I minus A over D denote my Laplacian. Earlier I had called D times I minus adjacency Laplacian. This thing is also Laplacian. That's fine. Abuse of terminology, but who does not abuse terminology? So yeah, that's my Laplacian. And I know Laplacians are PSD. So the eigenvalues of my Laplacian, I can denote them as 0, it's lambda 1 less than equal to lambda 2. I always call eigenvalues lambda for every single thing, and that confuses me in every single paper I am writing. Lambda kiska eigenvalue tha bhai? I forgot. So yeah, and 0 is always an eigenvalue of Laplacian, that you can verify. We verified that all the rows of the Laplacian added up to 0. Alright? Great. So given this Laplacian, my graph has 10 connected components. What can you say about lambda 10? So here is a claim.
Structurally is like 10 blocks.
Yes, yes, yes. So it implies that my graph has at least 10 connected components. At least k connected. In both directions. So suppose my graph has 10 connected components. How will you prove that lambda 10 is 0? I claim it's easy. Did anybody take a look at the note that Arka sent? Lecture 0, also called lecture 4. Yeah. So let's recall. Recall that x transpose Laplacian x is x transposed di minus a over d times x. And we already observed that x transpose di minus a was the sum over all edges of xu minus xv whole square divided by d times summation xv whole square. Think of x as a unit vector. That's an expression that you can write. The key thing to realize here, so if x is a unit vector, in fact you don't even need that summation xv square. That's the expression you will get. You can ignore the denominator, I don't care about the denominator. So notice that what I am doing is that I look at a connected component, I look at the x vector, and I look at the difference between the endpoints squared. That's all I am doing. I look at the difference between endpoints squared. So suppose the vertex x was constant over component 1. What is the contribution of component 1 to this quadratic form, to this value? So I have 10 components, right? So the question is that suppose x takes the same value over the entirety of this component. X is, let's say, I do not know, 1 over 10 everywhere on this component. Okay? Yeah, the contribution is 0. Okay? So that's the entire idea, that like, if I have 10 components, then I could find for you 10 disjointly supported vectors. 10 disjointly supported vectors. So the first vector is, let's say, 1 everywhere on component 2. The third vector is once everywhere on component 3. Fourth vector is once everywhere on that guy. On and on and on. So what I have produced for you is I have produced for you a certificate, right, with 4 different vectors in this picture, where all of those vectors are disjointly supported, therefore orthogonal. Right? Disjointly supported vectors are orthogonal. And all of those vectors have the property that this value, x transpose Lx, equals 0 for all of them. Right? So lambda k is 0. I realize that like those of you who perhaps need a much more solid refresher in linear algebra will like perhaps not follow these comments like as smoothly as you would like to. So to those of you who are like let's say struggling, I will recommend the following YouTube lecture series. So there is a lecture series by Luca Trevisan, unfortunately passed away. Brilliant scientist. So look at Ravi Jan's lectures on expanders. You can watch lecture 1. All the linear algebra background they will provide. So that's like one comment that I wanted to make. But still we are not done with that claim. That claim is 2 directions. I showed that if you have 10 connected components, lambda 10 is 0. If lambda 10 is 0, you have at least 10 connected components. That's what I would like to show. So maybe I should leave that as an exercise. What do you think, Alka? Who has seen the proof that if lambda 10 is 0, there are at least 10 connected components? The proof is written in my lecture notes, by the way. Oh, a few of you have seen. Alka, you have not seen it? Raise your hand then. And I would imagine that, there are a few more students who have seen this proof, but okay. Great. So now, what Cheeger wanted, so Cheeger is alive. So in a lot of situations, when you want some kind of improved algorithm for a certain case.
The lecture note you are referring to is the linear algebra lecture note, right?
No, so right now is referring to the lecture note for this class. I mean, I told the class, so this is for lecture 1. So the notes are,
Send them that.
that's fine, that's fine. I just expected that you would send a lecture note for lecture number 0. This is all lecture number 1. Yeah, so I'll assume that the reverse direction you will be able to prove it in an exercise session. Okay. Or at least the instructors here will be able to help you with that. What I want to do next is I want to think about the problem that Cheeger asked us to think about. So Jeff Cheeger was a differential geometer, a brilliant mathematician, like lots of accolades, proved what is called Cheeger's inequality. So Cheeger's inequality is a beautiful relaxation of what it means for a graph to be almost disconnected. Right? I mean, a graph is almost disconnected. If I use that phrase, you will imagine that perhaps there is a tiny little component over here, a component over here, and they are connected sparsely. That's exactly right. So Cheeger showed that an evidence of a graph being almost disconnected can be read off from the spectra, from the eigenvalues of your Laplacian matrix. I mean, just for a second, let it sink in. Just how cool is this? The graph was exactly disconnected. I could read it off from the eigenvalues. Lambda 2 being 0 means I have at least 2 connected components. A certificate of disconnectivity, right? Lambda 2, if lambda 2 is very close to 0, the graph is almost disconnected. So that's what Cheeger managed to prove. Okay? So let me write what Cheeger's inequality is. And pretty much so I feel almost embarrassed to say this, it's not just me but a few other people. When we are working on some projects, often our bottleneck is to improve the bounds that Cheeger got for us. But in my naivety, what I had written in my lecture notes is how to beat Cheeger. And back then Cheeger was 84 years old. So somebody saw my note, actually it was my advisor, and he was like, why do you want to beat Cheeger? So, okay. The theme is that if G is disconnected, the echoes of disconnectivity can be found hiding in the spectrum, or can be read off from the eigenvalues lambda 1, lambda 2, all the way up to lambda n. The theme is to relax this requirement. The theme is to say that if G is almost disconnected, then the second eigenvalue is almost 0. Even that can be read off from the spectrum. Then lambda 2 almost 0. It's positive semi-definite, so I know that it's definitely not on the negative side. It's some small positive number. That's the theme that Cheeger had. Let me state the statement of Cheeger's inequality now.
What do you mean by almost disconnected?
Great. So I will quantify this. Give me a few more minutes, I'll quantify this. So I'm going to define a quantity called graph expansion. Once I have the definition, I'll be able to answer your question. This is the second most important definition in this talk. The first most important definition was that of a Laplacian. The second important definition is graph expansion. So you have a deregular graph. For a subset of vertices, capital S, we define the quantity expansion of S to be the following thing. It's the ratio of the number of edges going from S to S complement divided by D times the size of S. In pictures, it kind of looks like the following, that you have some subset S of vertices. You have S complement. That's the picture. So what I'm doing, the numerator counts the number of edges that go from S to the complement of S. So here I have 5 edges going from S to complement of S. And I divide it by something. I divide it by the total number of edges incident to the vertices in S. I divide it by total number of edges incident to vertex in S. The thing is, why do I define it this way? It's because it gives you one way to think about the probability that a random walk started at a random vertex within S, so started at a uniformly random vertex within S, leaves us at capital S in one step. Right? So this is exactly the probability that, so you pick a uniformly random vertex in S, that a one-step walk from U exits S. Right? So that's expansion of a set. I have not yet defined expansion of a graph. That's what I wanted to define. So let me make the definition now. So in some sense, what I want to say is that, like, my graph has no bottlenecks. No matter which vertex you start from, no matter which set you start from, you will be able to escape that set fairly quickly. But there is something annoying here. What is annoying is that, like, it's easy to escape small sets. Like, should I be demanding you to escape, like, large sets? Right? So I don't want to, like, make it unfair demand, because, like, there is one vertex called vertex 1, and here is the rest of the graph. Right? So perhaps it's unfair to demand that you escape from the bigger side. So that's the caveat that I will use to define expansion. So the way I define expansion is the following. That the expansion of a graph is denoted as phi of g, and we say phi of g equals the set which kind of tries to hold walks within, the set with the worst expansion, the set from which the escape probability is the smallest. So it's the minimum over all subsets of vertices of size at most n over 2 phi of s. That's expansion. Okay. It's a very important quantity to understand. Like, the reasons are deep. The reasons are essentially related to Cheever's inequality that I will state very soon for you now. I'll be able to also tell you what almost disconnected means. So remember, at the beginning of this lecture, we discussed that if you have this graph, a complete graph where you start at vertex 1, at the next step where I am, you pretty much cannot predict it. The nice thing about expanders is the following, that so there are 3 regular expanders that we know how to construct. So it's a 3 regular graph. So in some sense, this graph should not be well connected at all. Right? It's a 3 regular graph. Just how well connected can they be? If I want to disconnect vertex 1 from the rest of the graph, I'll just delete all the edges. The expansion is a notion which tells you that, it's a well connected in the following precise sense, that the amount of effort you took to disconnect the smaller side from the bigger side was to delete all the edges incident on the smaller side. The fraction of edges that you deleted was 1. Right? You deleted fraction 1 of edges incident on vertex 1 to disconnect vertex 1 from the rest. So expansion kind of tries to measure, in order to disconnect the smaller side from the larger side, what fraction of edges incident on the smaller side must you delete. That fraction is always large. Then your graph is an expander. Okay? The big idea is that just like in complete graphs, you could not tell me after one step which vertex I am standing on. I was standing at a uniformly random vertex for all you cared. In expander graphs, after log n steps, you will have no memory of where I started. So in not too many steps, only logarithmically many steps, log n is small, think of log n as being small, you cannot tell me where I started. Right? That's why expanders are kind of nice. Okay, so here is what sense in which I meant the graph is almost disconnected. So again, keep in mind that lambda 2 is small. It will be helpful to parse the statement of Cheever's inequality. So Cheever's inequality tells you that for any graph G, its expansion is at least lambda 2 over 2 and its at most square root twice lambda 2. If lambda 2 is small, expansion is small. The graph is almost disconnected. Right. Lambda 2 is small, the expansion is small. By the way, just by staring at the form of this expression, what do you think? Which inequality will be easier to prove, which inequality will be harder to prove? The left one or the right one? Which looks easy, which looks hard? Sorry? Left looks easy, good. And right one? Looks easy? Okay. So right one is in fact the harder part, as you pointed out. And like that's the main content of Cheever's. Left one is like actually fairly simple. It's not that hard at all. So let's see how we will prove the left one maybe. Actually, I don't think that I even have time for the left one. So I guess the left one and the right one are left to my lecture notes. So I'll stop here. Questions?
Are there any questions? Okay.
How do you use this inequality in the context of approximation?
Oh, great. So Professor Nilhara has asked a very important question. How do you use this inequality when you're trying to come up with approximation algorithms? So the first answer is that sparsest cut is a very important problem in its own right for various reasons. And this gives you an approximation algorithm for sparsity. So you can get an approximation to phi g by just estimating lambda 2. Right? So you get a quadratic approximation to phi g. So that's one answer. But the other answer is that, like, expansion is a very important quantity in the following sense, that if your graph is not an expander, then you can split it into a collection of expanders. If you remember, like you were discussing some charging argument, right? So the idea is that on expanders you can very often invent algorithms for a whole bunch of problems. Just like you can invent algorithms for like graphs with bounded limits. Expanders is a very important class. So you can invent algorithms on expanders, and the notion of sparsity allows you to, it facilitates building divide and conquer inspired algorithms by breaking the graph into a union of expanders. And so that way you can also end up with some let's say approximation algorithms for a whole bunch of interesting problems. In fact, if you look at the literature in sublinear time algorithms, the area that I work in, so there are like a lot of algorithms, like you get a lot of FP tasks for very interesting problems, right? By cranking out the tool of expansion, the cranking out expansion tool. Yeah, I can give a detailed answer later maybe.
The other quick question is, does it make sense to us how you compute the stationary distribution? You just run it, or can you directly?
So for graphs, there is something beautiful that you can do. So Professor Nilhara has again asked one question that intrigues me a lot. So for undirected graphs, here is what you do. Pi of x for any vertex is proportional to its degree. I mean, so you can read out the eigenvector without cranking out an eigensolver. So that's just crazy. So whenever you have this situation that your Markov matrix satisfies detailed balance condition, if you know this. So very often what you do is that you design your Markov matrix to be reversible with respect to your favorite distribution. If it's reversible with your favorite distribution is the eigenvector, and you do not have to compute, you do not have to crank out an eigensolver. So, I mean, that's a very intriguing thing. Like if you want to look this up, you can look up Perron-Frobenius theory. But like you can even avoid Perron-Frobenius theory and just think from scratch. If detailed balance condition is true, you don't have to crank out Perron-Frobenius theory to give a very easy proof from first principles that pi of x is in fact an eigenvector. Other questions?
Any more questions? If not, let's thank the speaker. Here's a small group from CSS. So as usual, you know the routine now. Snacks are outside, coffee.
Can we start? Okay, welcome back to the second session of today, and Ramesh is going to give a very colorful talk this time. So over to you, Ramesh.
Well, thanks to all of you who showed up after the yesterday's talk. So I tested your patience with heavy technical content yesterday. Today we'll try with my poor handwriting. And if you are wondering what you are signing up for, this is the best it will get. So let's start. So today I'll be talking about coloring. So the references will again be, the standard references is the book by Williamson and Choice. I guess this is true for the whole summer school as well. So I'll not write the whole name, I'll just write the surname of the authors. Then there is a very nice book on semi-definite programming by Gartner and Motosek. There are various books by, sorry. Okay. So is this fine? This is fine? Okay. I'll try to.
No, from here I can't see anything actually.
Okay, then I think you'll need some people to come in the front. I can see a lot of empty seats. Because, okay, I'll try to write bigger. Sure. Yeah. And third is a set of lecture notes on course on approximation algorithm and hardness of approximation by Alantha Newman and Ola Svensson. Need to check this. Yeah. So okay, yeah. Let's start. Let's start with the definition of what does it mean for, like, I suppose all of you know what a valid coloring means. So given a graph, basically you need to find me an assignment. Okay, the assignment is a map from vertices to some, say I'm given some color C1 up to Ck. Okay, it's a map from vertices to 1 to k. Okay, such that the following is true, that fi is not equals to fj if I and j are connected in the graph. This is my notation for I connected to j. Okay, okay. I see already the font size has started to reduce again. Okay, so for example, I had this example here, but can all of you see this example? There is someone who can't see this example?
And the online audience won't be able to see that example.
Yeah, for the online audience, we'll explain to them what is going on.
Okay.
No, I don't really want to do this again. This is just one example with like, yeah. So can you see like how many colors are needed to color this graph? 3 colors? Are you sure? Four colors are needed, and okay, yeah. I mean, of course, we can do red, green, blue, yellow. We can do red again. We can probably do red again and probably do red again. Yeah. But does anyone see why 4 colors should be required in this case?
There is a click of size 4.
Exactly. There is a clique of size 4 formed by these vertices. Okay. Formed by this, yeah. There is a subgraph which is a clique of size 4, and you will at least need to color every vertex there differently. So we'll see this connection more strongly as we, yeah. I'll in fact get to that in a second. Okay. So firstly, let me define what is the graph coloring problem. We defined what is a valid coloring. Okay. So let's now define the graph coloring problem. It's basically to find a valid coloring for the graph. Okay, it's an optimization problem. We want to do it with minimum value for k possible. Okay, minimum k such that this assignment f is a valid coloring. Okay. Okay, so also this quantity, the minimum possible k, it has a very famous name. Does anyone here know this? I heard some voices here. Exactly, yeah. This is called the chromatic number of the graph. Yeah. It's called the chromatic number. And the typical notation used is chi of g for this, right? And there's a closely related quantity, which in fact we are just noticing some connection between that here, which is this quantity called, either you can call it clique number, but I'll call it independence number. It's just the complement graph, it's the clique number. Independence number alpha g. Okay, so and okay, so firstly, like yeah, we'll get into some connection between these quantities and what is the connection to graph, but okay, yeah. So firstly, let me start off with this result, which shows that. So this was various works. Like okay, firstly, like oh sorry, not 5 gig. This was how started in '99. And then I think this was a randomized result, and then Zuckerman in '06. They showed that both these problems, finding the independence number and the chromatic number, are like okay. There's no these are NP hard and stuff, but they also showed that you cannot hope to get. It's a very strong inapproximability result that you cannot get n to the power 1 minus epsilon approximation for these things in general graphs. Not possible. And this is like you may have seen or may see results in the school which are conditioned on the unique games, something called unique games conjecture. This is not even that. This is unless p not equals to np. It is not possible if unless p equal to np. Right? So a very strong inapproximability result for these problems. Yeah. So what can we really do? Notice that.
What is M?
Sorry, what is?
M.
Oh, where was m?
M power 1 is
Oh, this is n power 1 minus epsilon. Yeah. Okay. This is n to the power 1 minus epsilon. Okay. Yeah. Yeah. Well, you can like ask as many clarification. I understand the need for that. Okay. And what I want to now do is. Okay. So now, like yeah, you basically essentially can't do anything. Right? Notice that the n approximation is trivial for this problem, right? I mean, either for the independence number or the chromatic number, you can just return one vertex, or for the chromatic number, you can just color every vertex with a new color. Sorry.
What is the independence number?
Oh, yeah, sorry. Independence number is the size of the maximum independent set in the graph. I hope you know what the independent set in the graph means, right? No? Okay. So, okay, think about it this way, okay? So here I wanted to color every edge with a different possible color, right? So here I want, like it's a, you'll see the connection between these two. Let us say you are given a graph, okay? You basically want that to find a subset of vertices such that every pair in that subset do not have any edge with each other, okay? So for example, let us, for example, we can see in this trigraph, for example, what is an independent set? Well, this vertex we can keep it, and we can keep one of these, right? Because like, yeah, otherwise we will have, maybe we will keep this one. And maybe we can keep this one. If we keep the this is an independent set for sure, because these three edges do not, these three, like there is like the 3 choose 2 pair, there are no edges there, right? In the 3 choose 2 pair. Is this the maximum we can do in this graph?
Like
We can also keep this one. And I think 4 is the optimal thing that we can do here. So we can yeah. So that is the independent. So the size of the maximum independent set, the maximum such set is called the independence number of the graph. Notice that in the complement graph, it will be a clique. I can also ask for the clique number in the complement graph, which is exactly the size of the largest clique. This will be equal to the clique number in the complement graph, G bar. Okay. Right. Yeah. So as I was saying, like an approximation is trivial, right? So like you can For the independent set problem, you can return one vertex. Okay. The opt could at most be n, and alg value is at least 1. That's an n approximation. For the coloring, you could use a new set of n colors. Like you would just use n colors and color every vertex. There will be no this assignment will be valid assignment. But again, and this is an approximation because the graph could at best be an independent set. In fact, you can notice this observation. We write it here. Okay. That alpha g is at most chi of g bar. You see why this should be true?
Because if there is a click of size of that
Yeah.
size,
Yeah.
then we need at least that many numbers.
Just use this connection, right? Just use this connection, right? Alpha g is complement of g bar, right? So if you're talking about chromatic number of g bar, right? So alpha g is the same as the clique number of g bar, and as we were having, as we made this observation here, right? If you have a clique, you need that many colors at least, right? So that follows. So both of these are NP hard quantities to compute, but we have this inequality between them, and we'll see something like there is this computability issues with these quantities, but we'll see a computable quantity related to both of these later on in the lecture. Okay. So the coloring problem, it seems like you really can't make a lot of progress here, right? I mean, this is a very very strong inapproximability result that we have. So then people started doing the following. They started looking at a promise version of the problem. So what does the promise version mean? It means that I'm promised that the graph is, okay, so let me make a definition first. Okay. Let us say a graph is k colorable graph. Let me define that. K colorable graph. Okay. We say the graph is k colorable if there is a valid coloring, okay, with k colors. Okay. G has a valid coloring, valid assignment f from vertex at to k. Okay. So now what I'm saying is we are promised that the input instance that is given to us is k colorable. Okay. So now we want to maybe find the k coloring then, right? That could be one goal. Let us see. That is So can we do it for, hope to do it for arbitrary k, like k is not given as a part of the input? What would that mean if k is not given as a part of the input? Try to think about this, right? I'm saying,
It will be same as solving the original problem.
yeah, it will be same as solving the original graph coloring problem the way I defined it, right? Because k is, like any graph is some k colorable, right? It could be n colorable, but it's some k colorable, right? So arbitrary k is the same as old, same as the previous one. Same as old. Okay. So we really need to think k as a fixed input parameter. Okay. Yeah. You don't need the mic for that. You can just raise your hand. Just raise both your hands, so I understand what you're talking about. Okay. Yeah. No, I'm kidding. Yeah. Okay. Can you still see this? Akash, should we do something about this?
I think I need glasses now.
No. I'm talking about the light situation.
The light is power cut.
Okay. Yeah, I would again encourage few of you to come in the front so that because as I said, this is only going to get worse as we. Okay, let's see. So I'll try to do So far I haven't written anything very deep or anything yet. I'm just making some basic observations. Okay. So for arbitrary k, this is the same. So we really need to think of k as an input. Okay, like k is given to us as an input, and then we are trying to solve this problem. Then it makes sense. Like we are promised that the graph is, for example, some 7 colorable, and we are asking, okay, can you color it with as few colors as possible, right? So the goal is, the goal is to color it with exactly k colors for now. Let us say that is the goal, right? Okay. Yeah. I can wait if some of you have changed your mind after this. Right. So now the question is, okay, we are promised that the graph is, let us say, some 7 colorable. Can you actually color the graph with 7 colors, right? You would expect like this is should be much easier than the previous problem, right?
like we are given this k is given as an input in the problem, and yeah. So let us take small values of k and see what happens. Okay. So let me take k equals to 1 for instance. What does that mean? Graph is one colorable. So yeah, all the vertices are isolated, right? So of course we can always do that. We can always color the graph as one color. We don't do anything, right? This is of course done. What about the case of k equals to 2?
You have like a star configuration.
Like star configuration could be one possibility, but there could be more general class of graphs. Yeah, exactly. So these are bipartite graphs, right? Bipartite graphs are two colorable. This is a characterization of bipartite graph. And you can actually two color them by just alternating between them, right? You can two color them, right? So then the first non-trivial cases maybe when k is equals to 3. These are also you can call tripartite graphs. Okay, but what can we do with them? Like, can
we like choose one color and then we treat it as a bipartite graph?
Yeah. So what you're saying is I'll choose one color, okay, and I'll yeah. Actually, very good. Yeah. So you're already sort of yeah, but this you can't do it optimally.
Obviously.
Yeah.
We have to guess the first color.
Yeah. So there are issues with that. Okay. Yeah. So I'll just mention that this is a problem we really struggle with. Okay. So firstly, this is NP hard to do this. To even tell if a graph has a valid, the same problem is when the graph has a valid 3 coloring. Okay, we'll come back to the suggestion later when we're designing algorithms for this. In fact, most of what I say today, and most of in fact what the community does is also focused on only addressing this particular case, because we'll see. I'll tell you what is known about this soon. That already we are in much more trouble here. For example, this is known that it's NP hard to color this, and it's also known that. Let me check this as well. Yeah. So this was. I'll just add it here. This was a result by Sanjeev Khanna, Nati Lineal, and they made this observation that they showed that okay, NP hard to even find a 4 coloring of a 3 colorable graph. 4 coloring of a promised 3 colorable graph. This is also NP hard. Okay, and not only that, assuming some form of this unique game, some variant of a unique games conjecture, we also know that we do not expect big O1 approximation for this problem. Okay, like a constant approximation we do not expect for this problem. This is assuming some variant of a unique games conjecture, not exactly the unique games conjecture. This is a result due to Dinur, Mosel, and Audit Rejev from 2009. Okay, so what do we know about? Yeah.
So is it order of 1 or some fixed constant?
They show that okay. Fixed constant is not possible. Yeah. So they show that like if the graph is supposed to be 3 colorable, you can have any large. Another question?
Confirm what we are doing once again. So in promise version, we are given an input k and we are promised that the graph is
3 colorable. Yeah.
3 colorable, for example, and we have to return a coloring.
We have to return a valid coloring. Okay. And I also said that even deciding that if the graph is 3 colorable or not in general. I mean, of course, promise version you can decide it, but in general, even deciding a graph is 3 colorable is NP hard. Okay. So actually, let's So maybe our revised goal should be, instead of we'll still want a valid coloring, of course, but let us look at approximation guarantees for k equals to 3 because we sort of have to. So let's try to find a coloring, okay, from a vertex set, this time to some alpha k. Alpha is the approximation ratio, okay, and the goal is to minimize alpha while finding such a valid coloring. Okay, so we'll see what values of alpha are possible. Maybe let me. So first, make this observation that we notice that alpha equals to n is possible. Even in this case, you can color the graph with n colors, and opt value here is 3, right? Opt value is 3, alg value is at most n. So alpha equals to n is possible. Not really saying anything here. Okay. Yeah. Sorry. No, I'm saying that now can you color this with alpha times k many colors? Okay, the graph is promised to be k colorable. Okay, I'm asking whether you can cover it with some, like we notice that we cannot do with like, for example, we notice that alpha, like something like constant would not work here. Okay, but can you, for example, alpha be log n or something like let alpha depend upon n or anything. Okay, I'm just asking whether I can use much more colors than k and do the
Coloring.
a valid 3 coloring. Can I return a valid 3 coloring? Like this has to be a valid coloring. Like I'm not allowed to cheat on the constraints. I'm not allowed to skip constraints. I have to return a valid coloring, and I'll try to do it with minimum possible colors because it's actually hard to do it exactly. This should be our new goal, right? Is it makes sense clear?
Then the graph is k colorable, right? Where?
Yeah, we're promised that the graph is k colorable. Yeah, for the rest of everything I said today, we're promised the graph is k colorable. In fact, most of it will be focused on k equals to 3. Okay. So actually, yeah, let's look at the case of k equals to 3. Actually, this will work for any constant k. Okay. So like, yeah, the first observation is that there is a simple n approximation algorithm. Let me ask, let me say like there is a simple algorithm, some simple algorithm we want to design. Okay. Actually, let me give you the approximation guarantee that I want for this algorithm, and let me let you like try to see how you could do that. Okay. So alpha is n. I will go slightly smaller than n. I want an algorithm where alpha is n by log n. Like, okay, I should say big of n by log n. So n by log n. There is no n. I'll use maybe, yeah, sorry, yeah. This is also n. Okay, yeah. So yeah. Try to think about it. The approximation ratio should maybe tell you what you need to do with this. Also, I said this will work for 3 colorable running constant k. That is another hint. Has anyone here seen this before? No, very good. I'm surprised. This is okay, check that. This is a simple thing. There is no need to remember this. I mean, you can always construct it when you need it. Anyone, some ideas?
Do you pose the
break
question?
Sorry?
Is it like, do you partition the graph or like
Yeah.
break up the graph into like k units?
Yeah.
And then color each of them and get some some like divide and conquer kind of.
Yeah, very good. Yeah. Exactly, this is what we do, right? So look at the graph. Okay, break the graph into k pieces, and by construction, have each of the pieces be of size log n. I mean, I'm not saying like you just do it any partitioning. I'm not saying okay, this is okay, anything works. Okay, basically we are not going to assume anything about the structure of edges. I'm just going to do some partitioning and yeah. So what I want is that each of the pieces, okay, let us call this V1, V2, and let us call the final piece as VT. Okay, so I want each of the VI's to be like log n sized. Okay. Now, how do I solve the problem on each of the VI's? Yeah, exactly. Just enumerate, like we know the graph is 3 colorable or maybe some constant numbers colorable. Okay, so just for example, let us say 3 colorable, we just try all 3 to the power log n things. Okay, we know that the graph is 3 colorable, so the subset of it V1 has to be 3 colorable as well. Okay, and of course there could be like some edges there could be some like we just have like arbitrary partition, right? That structure between these could be arbitrary. We're not going to assume anything about those. So what we are going to do is we are going to run this algorithm, the polymer time algorithm. We are going to run it on each of the components, and we are going to use fresh set of colors for each vertex, right? So how many colors will you use? So what is the value of t? Because by construction we are having each component of size. So this should be omega log, yeah? Theta log, let us say. Yeah. And so t would be, if we go of n by log n, right? And yeah, so the L basically L can use fresh set of 3 colors, so it can get 3 times we go n by log n, okay, which I'm just calling it as we go of n by log n. Okay. While notice that the opt value, as it will be throughout all we discussed today, it is 3, right? We're promised that the graph is 3 color. So this gives you like n by log n approximation, right? Okay, good. So at least a simple this partitioning kind of a strategy gives you something non-trivial. But really, like, yeah, I mean, not really. Like you still, yeah, we still can't get n to the power 0.99. If we try to do that, this will become a sub-exponential time algorithm, clearly, right? So, so maybe, yeah, maybe we don't know. Maybe this problem is also as hard as the non-promised version, like the original graph coloring problem, where we couldn't get any n to the power 1 minus epsilon. But actually, that is not the case. We'll look at the idea that somebody suggested here, right? Which was that, okay, I'll get to the idea. Let me first note a few basic facts about okay, so firstly I want to take this is a basic fact, like a common interview question here as well. For example, the graph is maximum degree delta. Degree delta. Okay, you can color it with delta plus 1 colors. Okay, maybe this is not very legible, but yeah, this is exactly what I said is what I wrote. Okay, so if a graph has maximum degree delta, we can color it with delta plus 1 colors. Have you probably seen this before, right? I don't know if I've seen this before.
But so you just said that is going to be hard for 3 colorable promise.
No, so here I'm assuming that the graph is maximum degree.
Okay, sorry,
maximum degree delta, not the coloring is not delta. Yeah. Maximum degree is delta. Okay. Does anyone recall a quick proof of this? Greedy, exactly. Yeah? You just order the vertices. Okay. V1, V2, V. Okay, yeah. So first, like process them in this order. Okay. The first one we can give it any color. Then vertex V2 comes. Maybe there is an edge. Then we have to use a different color for this. Yeah, when you've all seen this before clearly, right? At any point, a vertex Vi, okay, we are interested in like it can at most have delta many edges going backwards because it has maximum degree delta. Okay, so there is always one color which is available for this, right? And we can color it. So in case this actually here is an interesting fact. Okay. Okay. So I believe Akash talked about eigenvalues earlier today. You can also look at the adjacency matrix of the graph. For simplicity, let us say it's a D-regular graph. Okay, you can also do it using alpha 1 plus 1 colors. Now this is the floor function on alpha 1. What is alpha 1? Alpha 1 is the eigenvalue of the adjacency matrix, the largest eigenvalue, lambda 1. Okay, lambda max I should say. Alpha 1 is lambda max of the adjacency matrix. Okay. Clearly, I believe you would see in this class that okay, alpha 1 is less than equals to D. In fact, the D regular graph is exactly D, right? Not exactly D. Oh wait, what I'm saying. Okay, maybe there's something over here. Okay, let me actually note it. Maybe you should ask this statement to me offline, but there is the same algorithm can actually be improved using eigenvalues. Let me not make that statement right now. I take that back. I should be using this one, I think. The second fact I want to notice, what your observation was, that if the graph is promised to be k colorable, okay, then the neighborhood of a vertex V, for some vertex V, like any vertex V, the neighborhood is k minus 1 colorable. So maybe to make it precise, let us say the graph is 3 colorable, okay, fix a vertex, I look at the neighborhood of that vertex, okay, I'm saying that neighborhood is bipartite. Is it clear why this should be the case? So what is, let us see a picture maybe. There is a vertex, okay. I'm saying, okay, let's define this neighborhood of a vertex. Neighborhood of a vertex V. And the rest of the graph sits here. That is G minus G, basically the rest of the graph. Okay. So this could be arbitrary, like of course. And of course the graph is k colored, I don't assume anything about that structure here. You could also have edges here. Okay. What I'm saying is that this neighborhood is k minus 1 color. In the case of 3 color, it is 2 color. Okay, just this graph, the neighborhood graph is only. And the reason most of you might have noticed is if you get put by contradiction, right? If the neighborhood is not k minus 1 colorable, it requires k colors. Okay. For some reason it requires those k colors C1 to Ck, then you can then V has an edge to everyone because by definition it is the neighborhood of V. Right? So it will require an extra color. So then the graph was not what it was promised to be, it was not k colorable even to start with, right? So okay. Yeah. Yeah. Okay, so we'll basically using this fact 1 and 2 and we'll be designing an algorithm for this problem. This is originally due to Avi Vigdason in 1983. Graph coloring algorithm. Again, everything is in the land where we are promised that the graph is k colorable, but we'll talk about it for k equals to 3 now. Okay. So based upon these two facts, so what do you think should be the idea? How should we try to use these facts? So notice what these facts are trying to say. Okay, if the graph is, for example, if the graph has a neighbor, for example, a 3-colored graph, some vertex has a lot of neighbors. Okay, it has very large degree, right? So this fact is sort of saying, okay, you look at the neighborhood, that you can color with very few colors, right? And this is sort of saying the other thing. Okay, if every vertex, because if some vertex has large degree, okay, large number of uncolored nodes, you can look at the neighborhood and color it. If a vertex has large degree, a large number of neighbors with uncolored nodes, you can use this to color it using just 2 colors in that case, right? So if there exists a vertex, you can do this, and if there doesn't exist any such vertex, if all vertices have degree small, you can also color the graph using small number of colors. Right? There is some sort of a trade-off happening already, you can see, right? These two ideas are both helping us in some regimes complement to each other, right? They are complementary ideas, and we should, and this is what exactly the observation that Wilkerson had, and here is the algorithm. Okay, so I'll specify a parameter t. It's a t algorithm, t alg. Okay, so the first step is if there exists a vertex, okay, such that so we start coloring it. Okay, for example, every vertex, if the graph is maximum degree larger than delta, larger than t. Okay, then every vertex is eligible vertex for the first step. Okay, in the first step we run a loop where we go over, if there is such a vertex, we loop over those vertices such that its neighborhood, okay, which is its uncolored neighborhood, okay, let me call that n prime v. Okay, this is the uncolored neighborhood of v. Okay, it has degree at least, there are at least d, this is a size at least d. Okay, the uncolored neighborhood, there are at least t vertices there. Okay, then I will do the following. I will color the vertex v, if there is such a vertex v. Okay, I will color this vertex v union this uncolored plus the uncolored neighborhood. Okay, I will color this graph, okay, using the step 2. Okay, and I can use it, color it with the t minus 1 colors, right? That makes sense. And at some point, this loop will terminate. We will have no vertex which is so every vertex will have this neighborhood less than t. Okay, what does that mean? The degree, the maximum degree is at most t, right?
Can that be less than equal to t minus 1 colors?
Can that be less than equals to?
T minus 1 colors or it is.
Yeah.
What was the question?
No, like whatever. T minus 1 colors.
Can you do
Can
it with
there
less?
be inequality?
Can it be an inequality? I suppose so. I suppose so. I would think so. Yeah.
Ramesh, how can you color the 3 minus 1?
We had this factor.
If they are not connected among them,
Yeah,
so
then
we can just
color
calculate
it one,
two.
two colors. Yeah. What is this factor?
But you are including the vertex here also.
Okay, good. So we can color it with t colors then. Yeah.
But T can be much larger than, much less than K.
Oh, sorry. Yeah. No, sorry. Wait, sorry. Yeah, sorry. I'm very sorry. I get your point. So we'll color with 3 new colors. Yeah. The graph is promised to student k equals to 3. Color with 3 colors, right? So this says that yeah. So k and t are different, of course. T is yeah. Sorry. So yeah, the t is supposed to be stand for delta here, right? Not for k. Yeah. Sorry. Thanks for correcting on that. So we can color V union this uncolored neighborhood using 3 new colors. Okay. I hope that makes sense, right? Like okay, yeah. I mean, in every iteration, we'll use new colors because we were not going to assume anything about this vertex and its neighborhood and some other vertex and its neighborhood. We are always safe if we use 3 new colors, right? I mean, there can be no conflicts, right? So we'll use
an uncolored vertex, not any vertex.
yeah. There should be a uncolored vertex.
Can you explain the algorithm?
Yes, I'll do that. So at some point the graph has some vertices colored. Okay, we pick some uncolored vertex. If there exists some uncolored vertex such that the neighborhood there are less than t neighbors. Okay, the uncolored neighbors. Okay, let me more than t neighbors. Sorry. Maybe let me draw a diagram. Yeah. So if there is some vertex V and we look at its neighborhood, okay, and the number of neighbors, yeah, so maybe some neighbors are colored. Let us say these neighbors are colored already. So from some previous step, and these neighbors are uncolored. Okay, I only look at the uncolored neighbors. Okay, and if there are more than t uncolored neighbors, okay, I know that I can color this graph using. Okay, let us actually make it 3 and 2. This may help. Having another parameter is confusing us. Okay, then we can color this using 2 colors. Yeah. The neighborhood we can use it, color it using 2 colors, and along with this vertex V, you can color it using 3 colors. Does that clarify things? I still see a puzzled look. I'm not sure. Yeah. So what I'm saying is, okay, yeah, maybe that having a parameter was confusing me. Maybe I was also confusing you guys as well. So yeah, we promise the graph is 3 colorable, then the neighborhood is 2 colorable, and then we are choosing some parameter t. So this t is something I'll choose later. Okay, I'll optimize for t basically. As I said, these two are complementary ideas, and the choice of t will be dictated by this. And this is a theme that we'll see a lot in graph coloring, other algorithms today as well. Okay.
How do we know the graph will be colored?
So the graph is 3 color.
Which color?
Sorry.
So how do we do the coloring?
How do we do the coloring? We use fresh colors every day.
How do we finish how do we know that it terminates?
Oh, how
Oh yeah. So this is while we have an uncolored vertex V.
And suppose its neighborhood is less than t?
Yeah, that is the second step. This algorithm is not yet complete.
Okay.
Yeah. So basically, if we are unable to find any uncolored vertex, okay, which has its uncolored neighborhood larger than type t, okay, what we'll do is we are in this case, right? The graph has to have maximum degree at most t plus 1, right? And we'll just use maximum degree t, and we'll just use t plus 1 colors there, right? So if let me say if no such vertex exists, no such vertex, color with the t plus 1 colors. Okay. So now, as you can imagine, if you set your t to be very high, okay, you will quickly end this phase, okay, just you will color some vertices and then you will be off, but then you will have to use a lot of colors, right, and yeah, and the other way around is true, right, if you like are very choosy, if you like don't want to use this algorithm at all, okay, then you will of course may require large number of colors, we are using 3 fresh colors every time here, right. So what is the right value of t? Well, that will just be decided by the number of colors that the algorithm uses. Let me call that the value of the alg for this particular algorithm. So how many colors does this algorithm uses? Let's take a look at that.
3 into number of iteration in the first one.
Yes, so how many iterations can the first step run for? That is the thing to answer, right? N by t plus 1, I think, right? Because we also have the vertex v, right? So yeah, the number of steps is this clear? Like how many steps can the first step run for, right? We have n vertices. Every time we are coloring that vertex, so this part becomes like colored now. Okay, t plus 1 vertices get colored every time. Okay, so this can at most run for n by t plus 1 steps, right? And every time we are using 3 fresh colors. Okay, so these are number of colors that is used by the first step of the algorithm. Okay, the number of colors used by the second step of the algorithm is just t plus 1, right? So this is our expression for the number of colors that the algorithm uses. Like for every value of t, this uses this many colors. So now we should decide what t to set. Can you see what t we should set? So that this is minimum as minimum as possible? No, to minimize this expression.
Oh, no.
Yeah, so then you can use AMGM or various way to prove it. Yeah. So yeah. Does everyone see that t has the t root n actually optimizes this expression? Yeah. So t equals to square root n, and for the value of square root n, the number of colors that you get, the value of the algorithm is also square root n. Okay. Opt was 3, right? The graph was promised to be 3 colorable, so again we have a square root n approximation for this problem. Okay. Do we have time? It's 12:15, right? So half an hour. Okay. Is there any question about this algorithm? The idea is very simple, right? I mean, we just noticed these two facts. The graph has, all the degrees are small, then we can color it using this idea, and then if the graph is, if some vertex has a large neighborhood, okay, then that neighborhood is 2 colorable. So you make, yeah. So this is what, like formally, like people started noticing this is an idea of progress, okay, and right. So in both sense you make progress in this case, right? So square root n you could get, and let me now, maybe I'll not write this stuff, I'll maybe just mention what all people can do. Firstly, this would be an exercise question. I mean, I don't know whether we have tutorials today, but anyways, I just mean to like for you to work it out. So what about k colorable? What do you think we should be able to do? So that's an exercise question. You should try to, maybe I'll write it here. Okay. For any k, you can, this is the same paper where it doesn't prove that, you can get big O of k times n to the power 1 minus 1 over k minus 1. Okay. So for example, try to do it for k equals to 4. You will get n to the power 2 by 3 for k equals to 4. Okay. And you will see the bunch of ideas, the bulk of the ideas are, you will already see for the case of k equals to 4. There is some sort of, we want to do this thing, but we somehow want to do this recursively. So yeah, that's an exercise question. So now I'll tell you how the progress happened on this problem. I'll not write this part down. Yeah, for k equals to, let us focus on the case of k equals to 3. So it doesn't give the square root n algorithm. So then there was like a bunch of papers, some by, yeah, maybe I'll not write down the authors as well. Some of these had Victorson again in it, and these were like, they're able to give square root n by log n. They're able to like shave another factor of square root log n from this. Okay, and yeah, so and also like people they were using this similar idea, some like, ideas on top of this, but people also realize that this is sort of a bottleneck. Like with these ideas, you cannot do much better than this. And then, like Abram Blum in 1994 gave a n to the power 3 by 8 approximation algorithm for this problem. Okay. Yeah. So again, the idea, I'll not go into the details of this algorithm. Okay. Yeah. So the idea there was that you look at two neighborhoods of a vertex. Okay. So here we are only looking at a neighborhood. You look at the neighborhood of a neighborhood of a vertex. Let me try to like give some intuition again why this may help. Okay. Yeah, let's go ahead. So the way the way to see this is, okay, let us say you take a random 3 colorable graph. Okay. The random 3 colorable graph. What do you mean by random 3 colorable graph? Like there is a probability that there is an edge is you just add an edge between these color classes with probability p. Okay. So p is like whatever. Let the graph have average degree d, so p is like d by n.
So these color classes are fixed in advance?
Yeah, so let us say they are fixed in advance. And let us also assume, like we are going to make a bunch of assumptions, so this is only for motivation. Let us say that all of them are equal sized. Each of the color class is like n by 3. So the idea is, if you look at, let us say this, let us call this red, let us call this green, let us call this blue class. Okay.
How do we assume that a random graph is 3 colorable?
Sorry?
How do we ensure that a random graph?
No, we first, so here is the generation process. Divide your vertices into 3 color classes of equal size, okay, and randomly add edges only between the color classes. It's not a random graph, it's a graph that first fixes the 3 color classes and then you add edges randomly between the color classes with probability p. Okay.
So we know in advance where
The graph is 3 color.
the person providing us the graph knows
Yeah.
what colors.
Yeah.
to
So
use.
this is just for motivation. This will not we don't actually need randomness for this algorithm. So that algorithm by Blum is actually the worst case. I was just trying to motivate it by looking at a neighborhood of a vertex will be helpful. And the motivation I'm going to do is through random graphs. Okay. So the point is that if you fix a vertex, okay, which has red color, okay, and if you look at its neighborhood, okay, what do you expect? You expect to see like half of the vertices coming from G, half of the vertices coming from the blue set of vertices, right? Which is okay. I mean, okay, maybe I should draw it like this. The neighborhood is like roughly half of the vertices are coming from here, half of the vertices are coming from here, okay. But now if you look at a neighborhood of neighborhood, the distribution over the, look at the vertices and neighborhood of V. What is the distribution there? Like how many vertices? Here the distribution was in the neighborhood of V, none of the vertices will come from red, half of them will come from green, half of them will come from blue. Right? What do you think is the distribution there? Like roughly? Yeah. Well, no. Let's see why. So, like the neighbor, roughly half of the neighbors are in green, half of them are in blue, right? So, yeah, half of them are in green. So let us look at their neighborhoods, the ones that are in green. Okay, let us, earlier we had half of these are green, half of these are blue, right? These were green, these were blue. Now we are looking at the neighbors of these, right? So for these neighbors, we expect roughly half of them to be from red, and half of them to be from blue, right? For a green vertex, we expect this to be blue, right? And for a blue vertex, we expect half of them to be from red and half of them from green, right? Now if you, now can you see what the distribution is going to be, roughly? The red vertices are going to be like half, because they, and a quarter for each. Okay? Okay, so so there are a bunch of properties. So again, this property uses some randomness, right? Why does this property help us? Because it tells us that we have a if you look at the neighborhood of V, we'll have a huge independent set of size at least half.
So we get to know about the vertices which have higher degree.
Yes. So that is another part. Okay, that helps if the vertices degrees if the vertices degrees are too small, for example, like I don't want to go into all the details because I want to also get into talk a bit about the SDP algorithm. But the degrees are much smaller, then you show that alpha g is anyways large. If the average degree is, let us say, smaller than n to the power. So what is the claim that he shows here? This you can show formally, and I do have notes of it, but I don't think I will present it. You can show that in such a random graph, you have an independent set of size n to the power 2 by 3. You can find an independent set, and you can find this in the neighborhood of V. You can find such a large independent set. Okay, if you can find such a large independent set, you would expect to recurse, right? You can remove this independent set and try to do these things again. There are issues with that. What I wanted to say is that okay, you can at least to start with have a large independent set in this neighborhood of V. Okay, so there are other properties about neighborhood of V that he notices, which is that it is much larger than neighborhood of V. Okay. Again, this is something if you think about it carefully, this is what Akash maybe Akash didn't talk about this, but it's like a boundary expansion of this set. But so the point is I'll not talk about. I just wanted to mention this idea. I'll not talk about this in detail. The thing is that you can get n to the power 3 by 8 from this using these ideas. In fact, you can get much better here, but you can get something like n to the power 1 by 3 here. But you try to translate these ideas to a general graph. So basically, you observe that okay, you need this property and some sort of this distribution property you need to do. Okay. Yeah.
Can you speak like slow or
Okay. No, so I understand that. This takes a time to figure out. I don't want to get into too many details here. That is the point. I just want to, at a very high level, mention the idea. So I'll not do the calculation. I'll just say that the neighborhood of V has a large independent set, and that is better than looking at the neighborhood of V. Okay, that helps, and this helps us to get down to n to the power 3 by 8.
That's not true for any graph, no?
It's not true for any graph. I just showed it for random graph. But what Blum does is
random graph, like you have like n by 2, like theta.
Yeah.
Okay. So this n power 2 by 3 is for what kind of graphs?
No. So what I'm saying is the neighborhood of V, but it's the size of that. That doesn't have size n. That has size roughly d square. If d is the average degree here, like let us say every vertex is roughly d irregular, right? So then it has like d square neighbors,
Right.
Okay. And I'm saying in those I can find like n to the power 2 by 3 sized. You would say this would only be possible if d is at least n to the power 1 by 3. But I earlier argued that d is smaller than n to the power 1 by 3. Then you can greedily find a large independent set. Okay. So there are two cases. If d is smaller than n to the power 1 by 3, okay, you can greedily find a large independent set. But just there is a large independent set, you can just greedily find it. And if that is not the case, then this gives you a large independent set. Okay. I understand this is very sketchy, but okay, maybe I should. That is my cue to maybe then switch to other stuff and not talk about it at all. Maybe So basically, this idea helps. That's all I wanted to say. Okay. So we have 20 more minutes. This claim remain. Right, so now I'm going to define some quantity which is called vector 3 coloring or vector k coloring, if you want to say it. Okay, so what is a vector coloring? It is a map from vertices to, now we are mapping them to a sphere. Okay, let us bring the sphere back. Okay, unit sphere, and the graph is, so we want to do the following. Okay, this is the definition. Okay, that for a vertex I and j, Okay, there is a map. Okay, we'll call this map F, right? So Fi transpose. Now okay, maybe I should use a different one because now I want to think of these as vectors. Okay, let me use gamma i's. Okay, this is to the sphere. Okay, such that Fi transpose Fj is equals to -1 over k minus 1 for all edges in the graph. This is the definition of a vector 3 coloring. Okay, we say a vector k coloring. If you want to say, okay, for 3 coloring, this would mean that I want Fi transpose F. So okay, maybe let us start for k equals to 2. What does this mean? For k equals to 2, this is saying that whenever there is an edge, I want to assign the vertices so that their inner product is -1. Okay.
Ramesh, the mapping is from like vertex side
To a sphere, a unit sphere.
Sphere means like you're including the inside as well. Or like,
No, I'm just talking about the bound.
okay. Okay, not
Not the ball. Yeah.
and that is like gamma I.
Yeah, that is gamma. Yeah, we'll get rid of it soon. Yeah, this is gamma. Yeah.
So okay, so there is a map and like what are Fi's?
Fi is okay. These are gamma i's. Thank you. Gamma I transpose gamma j is -1 over k minus 1. Okay. So what I want to first say is if the graph is promised to be, let us say, 2 colorable even. Okay. Can we always find such a map such that this is true? Okay. I'm asking, can you embed the vertices of the graph into n dimensions so that this is true? Should we think about this?
you need the dot product to be
-1 for every edge in the graph.
So
So k equals to 2 means the graph is bipartite, right? So I can just put, the graph is actually a bipartite. So this has 2 pieces, V1, V2, right? And there are edges only go from V1 to V2. Okay, so if I put V1 as this point on the sphere, which is 1, 0, 0, 0, this point, and if I put V2 as this point, which is -1, 0, 0, 0, right? I can actually satisfy this coloring. Okay, so whenever there is a coloring, you can always find a vector k coloring. So in that sense, this is a relaxation of the problem, right? For any coloring, I can find such a vector k coloring. Okay, notice that the vector coloring also has a parameter k inside it. Okay, this will be important later on. Okay, can we do it for 3? So can I assign? So what does it mean to do it for k equals to 3? So the graph is promised to be 3-partite, right? K equals to 3. There are 3 color classes, right? Let's do this. Can I give vectors so that,
how is this visualization with that circle helping us?
that is a sphere.
Yeah, sphere.
Yeah. But for k equals to 2, it is actually maybe, that is true. It may be misleading us, but okay. Yeah. You get it. Yeah. But it is. I want to draw a sphere basically.
Okay.
Yeah. This is not a circle.
Can we try
1 by root 2. Yeah, we can do that. Here 1 by root 2 and -1 by, yeah, that would work as well. But in fact, that is like if you want to do it, I'll get to that. Okay. There's a formula that you can write for this. But the question is, for k equals to 3, can we find such a mapping? Can we assign some vectors in the unit sphere?
There's some 60 degrees in between them.
Not 60 degree, but 120 degree. 120 degree. Right? We can assign some vectors which are like this on a sphere, right? They are like forming an angle 2 pi by 3. Okay, and then you can check that, So for any valid k coloring, so for any, if the graph is promised to be k colorable, you can always find such a valid k coloring. Okay, that's what I wanted to say.
Can you go over the reduction once again?
Yeah. So what is a vector k coloring? Okay, the vector k coloring says that you want to, So we are promised that vector k coloring says that can you find me vectors? Okay, where each of the vertices is like this is as far apart I can. Okay, well, let us say k equals to 2. Okay, how far can 2 vectors be? They can, like the unit vectors. Okay, maybe this is something I want. Yeah, these are unit vectors. Yeah. because I am trying them on a unit sphere. Right? How far can two vectors vectors be on a unit sphere? Okay. Yeah, minus like 180 degree apart, right? Minus 1. Their inner product is minus 1. Okay. So the vector 2 coloring problem is asking, okay, can you find such vectors? Can you embed your graph, the vertices of the graph, into a unit sphere so that for every edge the vectors are as far apart as possible? Okay. Well, it is not like, yeah. So we clearly see that there is one way to do that. The graph is promised to be 2 colorable, which is just assign all the vertices which are on the one side, V1 side, assign them this vector, and assign like this vector, 2 vertices in V2. Then whenever there is an edge that could only be between V1 and V2, they will by construction have these 180 degree angles. So you can always find a like this coloring, like a vector K coloring for a 2 colorable graph. You can find a vector 2 coloring. Of course, this will find like there is nobody restricting it to do it this particular construction. The only constraint it has to satisfy is the angles have to be antipodal. Like the vectors have to be antipodal. And it can do it in like whatever fancy way it wants to do. Okay, the vector program is it's optimizing over a much richer class of things. Okay, the reason we are doing this is because earlier we noticed that both these quantities are we cannot compute them. Okay, so now I want to maybe find a relaxation to a quantity that we can compute, and that is why we are doing this vector K. That is where this is coming from. Okay.
So for this particular thing, we only need a circle, right? So is there a reason why you're using a sphere?
No, so we are, yeah, you need an n dimension, yeah. Maybe a circle is actually confusing things. So why should we be able to solve it efficiently even? Okay. In some sense, this goes back to what I was saying yesterday. Okay. Why is vector programming solvable? Always all the vectors have to live in n dimension space. If you are solving an SDP, so-called, like this is an SDP, like I'm hiding the SDP today. Okay. But this is an SDP, and like yeah, this finding such a vector K coloring can be written as an SDP relaxation, and it only works if you allow like the dimension to be n dimensions. Like the reason sort of is that if you don't do that, then the PSD matrix you are putting a rank constraint on that, which is not a convex constraint. If I have two matrices X and Y whose rank is at most, like let's say and rank is at most n by 2. If I add X plus Y, that doesn't necessarily need to have rank n by 2. Okay, adding a rank constraint is not a convex constraint. Okay, but we want convex program because we can efficiently solve those. So if we let the vectors live in Rn, the rank will be n. Okay, like yeah, if I add two matrices of n by n size, like the rank even after adding them would be at most n. So the rank, we can drop the rank constraint there. We can safely drop the rank constraint there, and then we can solve it without the rank constraint. So we really need the vectors to be in n-dimensional space to actually solve this program. Does it make sense? Okay, so maybe let me actually define this function. Okay. This is called the log theta function. So here I will define it more generally. Okay, I will say minimize t such that L dot Vj equals to -1 over t minus 1. By the way, yeah, this is actually written more in like the SDP vector programming form. But let me ask you a question. So what is the most general way to see this? Okay, for k equals to 3, you could do it 2 pi by 3 apart. For a general k, how do we get this? How do we get the? How do we get these? No, yeah, not 2 pi by. Is a name for this? Sorry? No, roots of unity also. Something else. The geometric name for this thing. How do we generate all these? Maximum, like the inner product here is like between any two things is -1 over k minus 1. Between like you have to find some vectors u1 to uk such that the inner product between them is -1. Yeah, no, I want to ask the question first, like, yeah, maybe, yeah. Yeah, so actually, yeah, you can do it using this simplex. Okay, so, how do you draw simplex? Yeah. Yeah, if you take the center point and like these be the vertices of simplex, and there is a very nice linear algebraic equation which I'll skip writing, but there is a very nice way, like, Similar to how you do Gram-Schmidt orthogonalization in linear algebra, there is a similar formalization. Like you can write something like the vector ui's. So here u1, u2, u3 are these vectors. You can write ui as some, like you can write some sort of a linear relation similar to how you get for Gram-Schmidt orthogonalization. You can similarly write such an equation to generate these vectors of a simplex. Okay. So this is the lowest theta function. Okay, we just noticed that if the graph is k colorable, you can actually get t equals to k. Solve this for t equals to k. So now it should be clear that
Just to confirm, in the constraints, is that V or is it gamma?
this is v. I'm sorry. Yeah, this is v.
We are taking inner product of the vertices.
Good question. Let us change this to u.
Use a vector, right?
Write the SDP a bit bigger, right?
Okay.
I guess got it enough, I guess.
So U is a vector, right?
Yeah, this is a vector. For every vertex vi, I can assign a vector ui.
So it's the same thing as gamma.
Yeah, that is what exactly I was observing. That that there is some mapping. That was just a definition defined more generally. Basically that says that the argument that we made right now, that we can find a vector k coloring, we'll exactly use those vectors here. Okay, and we can actually match. So basically what we have said is, okay, so there is one thing here. This constraint I have not written it properly. This is defined for all ij not in the edge set of the graph. Okay. Here we were defining it for all edges in the graph. So to make this connection formal, we'll need to look at the complement of the graph. There we would have these edges. With the edges that are missing, there we would have those edges. Okay. So what the connection I'm making is, what we showed is that this coloring, finding the chromatic number. Okay. This is a relaxation of that problem, right? So this can, for any k coloring, okay, this can exactly get t equals to k is possible. We just showed this construction that t equals to k is possible. But this can actually do even better than that. So theta of g is actually less than the chromatic number in the complement graph, because I added the note constraint here, right? So earlier we had this equation. Okay. Now we are showing that, okay, this is still true. Okay. But we have also found this quantity theta of g, which is the lowest theta function, which is at most this chromatic number in the complement graph. Okay. We can, we don't have time for this today, but we can also show that theta g is actually sandwiched between the independence number and the chromatic number. So although we couldn't solve, these are NP-hard quantities, we could find this function theta g, which we can efficiently compute because this is vector programming. And we yesterday talked about this connection between vector programming and solving huge linear programs. This is the same thing. Okay, because of that connection, we can actually solve this. We can actually find these vectors. And so the interesting thing is, if so theta g is sandwiched between the independence number and the chromatic number in the complement graph. Okay, there are graphs. Sorry, theta g is this lowest theta function value. The value of this. What does it signify? It signifies what it is just this quantity, something sandwiched in between these. So it's a relaxation of both the problems. It's also a so I can't do this today, but there is also a natural relaxation that you can write for an independent set problem. Okay, that relaxation is also equivalent to. I'll not write that relaxation because it takes some time to write it and explain it. Okay, but it relaxes both the problems.
So you haven't defined the lowest theta function.
This is the lowest theta function.
But
the value t that you the value t that you optimal value that t that you get, that is the lowest theta function. This theta g is mostly overloaded in literature as well. We'll call this theta g, and also the value is called theta g. But that is what I meant, right? Okay. So this is the lowest theta function. It relaxes the independent set problem. Okay. In the independent set problem, you are trying to find a maximum independent set. It is a relaxation because it even looks at larger sets. It always finds you something which is larger than independent set, and also it relaxes the coloring in the complement graph. So it's a relaxation of both the coloring and the independent set problem. And there are graphs. These are called perfect graphs, where these two quantities are equal. So there, by this connection, we know that you have exactly found the independence number or the chromatic number, and so you can do this with SGPs, and finding such thing without SGPs, the shortest proofs that we know are at least more than 100 pages long. So this was a big thing, like for because these capture like rich class of graph, for example, chordal and interval graph, and all of these can be showed. These are of course for these interval graphs or chordal graph, you can actually compute colorings much faster. But in general, these capture a rich class of graphs, perfect graphs, weak perfect graphs. Like I'll not go into those details. But for those problems, because this is sandwich in between, and we earlier showed that alpha g is less than theta g. For those graphs, this is equal to theta g. That means that all of these inequalities have to be tight. So that means we can use theta g to compute the independence number as well as the chromatic number in such graphs. Okay, so good. This is a important quantity. So I wanted to find that some time on this, but now I just want to briefly mention about how do we improve that coloring. Like we have n to the power 3 by 8 Veblen. I probably have 5 minutes for that. So maybe I'll just hand way through this part without flashing many details. So yesterday I talked about this. So basically we now have this function, right? We now solve this function. Okay, we were promised that the graph is 3 colorable. Well, if we promise the graph is 3 colorable, we can probably this t was supposed to stand for k. We probably don't need the objective function then, right? So we can perhaps write this part. We can perhaps write this SDP where we don't need an objective function or a vector program, where we just have that ui dot uj is equals to -12 and norm of ui square is equals to 1. And for all I j which are edges in the graph. So this is the SDP. Okay. What does this SDP try to do? Like the idea is going to be the same. Okay. I'll repeat this idea again because I think I really like this way of this is somewhat of a mystery to me. Like when I see this SDP, when I was seeing this first time, why do we just use a random hyperplane and it works, right? The idea is okay. The vectors. So what is this SDP trying to do? Okay, the SDP is trying to put the vectors far apart from each other. Okay. For example, it tries to give an angle of 120 degrees if there is an edge in the graph. Okay. So for example, if some is here, it will try to it's a hard constraint, so it will have to satisfy this. Okay. Okay. And right. So the idea is okay. If the vectors are far apart, if we just try to take a random hyperplane that will cut this, which passes through the origin. Okay. It clusters the vertices. Some of them go to the right hand side, some of them to the left hand side. Okay. And we can try to argue with that probably this part, the vertex that we get on the left hand side is it is independent set. Okay. Why? Because in some sense if it has done a good job, okay, it would try to put vertices which are far apart from each other, right? So this is the intuition. Okay. But why do you use a random hyperplane? Why do you use you should find of course you can't find there should be some hyperplane which actually separates these out, right? We would expect such an hyperplane to exist because the vector program is trying to assign these vectors far away from each other at an angle 120 degree far away from each other. So we would expect some hyperplane to cut it, but algorithmically we don't compute that hyperplane. We just take a random hyperplane and cut it. So why does taking a random hyperplane work? So this has something to do So there is some intuition I can give for this, which is that if we have some data point in our n dimension. Okay, I talked about this yesterday. I don't know how many of you got this, but that's why I want to briefly mention this again. If I want to, reduce its dimension to a single dimension, there's some n-dimensional data point. I want to only save one dimension, one feature out of this. Okay, here is a construction which may look very weird, but if you take a random Gaussian vector, which is just take every entry as a normal 0-1 random variable, g1 to gn is a vector. Okay, each of these are normal 0-1 random variables. Okay, this is in some sense a good 1D map in the sense that it is an unbiased estimator. So this is a map which takes a vector and outputs a number. Okay, it takes a vector and outputs a number. Okay, so whatever the length of the vector was is under this map. It's a random map because G is a random vector. So the expected length of the vector phi of x is roughly the same as it was. And this, I said, was an exercise question. You can try to prove this. In fact, if you heard about the Johnson-Lindström lemma, it kind of does these with more dimension. Yeah. So if you want to do JL lemma in one dimension, this is sort of what you want to do, right? So in some sense, this is really what we want to do. Like these vectors in n dimension have some information, right? They have some information about, like they're trying to, like for an edge, they're trying to be far apart from each other. So that information is there, and well, we want to round them to one dimensions, while we want to preserve that information. And this is sort of the intuition, right? If you want to preserve that information, you should take a dot product with a random Gaussian. This lemma, if you prove this, sometimes it preserves something about that information. The norms and inner products are like, you know, related in some sense, and it somehow preserves this information about the vector that they had in the higher dimension. Why do we need to project them to one dimension though? Because eventually we need labels, like even for example in a vertex or problem, right? If you have numbers between, you know, the numbers can be any number between 0 and 1, you round them to 0 or 1, right? Eventually you need a 0 or 1 to solve the original problem. So that's why n-dimensional vectors are good, we can solve them efficiently, okay? But now you really need numbers. And the best way to map them is just to take a random Gaussian, like a inner product with random Gaussian, that sort of preserves some information about this vector, you know, some length information. And we can hope that even here there is some information in the vector program. It assigns vectors with the color classes far apart, and that can be captured. And I'll just wind up. So so this is the idea. Okay. The concern here is that so for max cut, for example, we did this. We took a random hyperplane and we got a cut. Like for example, we got some vertices on one side. We put the rest of the vertices on another side. You know, it was fine if some vertices are also within the same color class. I mean, we don't get the cut value for these edges, right? But it is fine. Like the program doesn't like say it is a valid output, right? But we can't say the same for coloring, right? For coloring, we would expect even in the max cut problem that there to be like the edges, most of the edges we want it to be cut, right? Because we have this constraint, right? Like the objective function is trying to pull them apart, okay? Similar to what we are trying to do here with this constraint, okay? There also the objective function is trying to pull them apart, okay? Right. But there we don't cry if we get an edge here, right? We're happy we just don't get the cut value. But for coloring, this is not okay, right? Coloring is a hard constraint. So if I have a constraint, like, there can be no edges in the color class, okay? So if by chance, if I just take a random cut, you will, even though the SDP should cluster it exactly, but it need not do that, okay? And then you may by chance get some edges, and you have to do this cleanup step after this, and that can take. For example, one idea is you just take t random hyperplanes, okay? Take another hyperplane, The whole space is divided up into 2 to the power t regions, okay? And you can show that in each of the regions, the probability that two vertices an edge comes gets small enough. And once this probability that edge gets like there is an edge in this region is small enough, you can sort of I'll not define what small enough means, but you can use some order log and extra colors to actually color the graph. If you can find and this is how this SDP manages to get n divided by 0.38 colors. This actually doesn't get n to the 0.38, but you have also to do this Wigderson, this balancing trick. Okay, so for all these SDBs, people do these tricks after, like from SDB you get something, and then you balance that out with the fact 1. Okay, and that gives you some, this was n to the power 0.38. In fact, this is worse than what Blum proved. Okay, but we didn't prove that, so for us this is the state of the art. There has been some progress, but the progress is still, for example, let me just write these names. So there was firstly this work this SDP that I just described. This is again by Kargar, Motwani, and Madhusudan. This was from 1994. Then they had another SDP, like the same SDP, but they analyzed it in a different fashion. Instead of taking T hyperplanes, they did something else, which they showed gives n to the power 1/4. I'm hiding some log n factors here. Okay, so n to the power 0.25 approximation, and people have been slowly making progress on this. For example, one progress I like is by Clamtech 2007, which gave n to the power 0.21, improved by a factor of 0.04 here. Yeah, and recent progress is actually from, I think, last year, where, yeah, so where they get, where they get n to the power 0.1747. Sorry, 19747. Right. So really, like we promised that the graph is 3 colorable, and this is the best we can do. And this constant have been like we've been slowly improving this constant, but the even assuming the like these conjectures, unique games conjecture and stuff. In fact, a variant of unique games conjecture, the only hardness result is you cannot get a constant approximation. So even log n is not ruled out. Okay, and the best you can do is like really bad. You can only get n to the power, some bad constant there. Right. I think I'm out of time. I'll maybe just mention. Right. So I guess okay. So for many of these optimization, I'll just mention one remark and I'll stop then. So many of the optimization problem, I think of these as like the progress happening in like 3 stages. Okay. Firstly, like before STPs. So for example, for a reference stage, like the sparse cut problem, or there are other problems. Like I'll not mention those problems. I just want to make this analogy that so the first generation of progress was like people trying like combinatorial ideas, linear programming before this Gomez-Williamson algorithm started doing STPs. So there was some progress that happened in the first generation, which in this case was the progress that happened with this Blum's paper, improving this to 10 to the power 3 by 8. And similarly for other problems, you can define such a notion. And then there was this second generation algorithms which started using SDPs. They started getting even better approximation guarantees. And then there are like these new third generation SDPs which are like SDPs in some sense. Yesterday when we were seeing SDP, we were trying to write some polynomials of degree 2 and writing constraints from there. People started asking why not higher degrees. Okay, and it started getting bigger and bigger SDPs, and that is like the third generation of progress on these problems. Unfortunately, the progress here hasn't really been that much, and even in like if you compare other problems, like you get huge progress. Somehow it hasn't been the progress hasn't been that drastic in coloring, and sort of the reason is that coloring is a hard constraint. So for example, there are structured instances. For example, what do you mean by structured instances? For example, a randomly generated instance or something like that. There is a lot of structure. So even like SDPs tend to struggle with those. Oh, sorry. The 3 coloring problem, we tend to struggle with those. While for other kind of problems, which are called these CSPs or like problem like max cut, where we are having an objective which we want to maximize, but it's fine if we mess up a bit. Okay. Their SDPs seem to actually help a lot compared to the normal algorithms. While in a coloring we have this really hard constraint, and SDPs sort of struggle with this. SDPs or any algorithm sort of struggle with these hard constraints. Like you have to really return me a color classes where there is no edge, which is in between these things. So yeah, so I think let's stop with that.
We'll take the questions offline. We are already over time, so let's go for lunch.